In November of 2017, a team of physicists published a paper in the journal Nature announcing that they had found something inside the Great Pyramid of Giza that no one had known was there. Not a tomb, not a treasure, not a passage that had been sealed and forgotten. Something stranger. Something that challenged the assumption, held for more than a century by virtually every Egyptologist on Earth, that the internal structure of the most studied building in human history was fully known and fully mapped. What the physicists found was a void, not a chamber in the conventional archaeological sense, not a room with walls and a ceiling and a floor, but a void, an anomaly in the density data, a large, empty space hidden deep within the massive limestone body of the pyramid, situated above the Grand Gallery and well below the outer surface of the monument, roughly 30 meters long and of uncertain height and cross-section. A space that had been sealed inside the limestone mass of the pyramid since the day the final casing stone was placed, more than 4,500 years ago. No human being had entered it. No human being had seen it. No human being had even suspected its existence until the physicists pointed their detectors at the pyramid, and the data came back, showing an absence where there should have been stone. The discovery was made not with shovels or drills or the traditional tools of archaeology. It was made with subatomic particles. The physicists had used a technique called muon tomography, a method that exploits the properties of muons, high-energy particles created when cosmic rays strike the upper atmosphere, to see inside solid structures without cutting into them. Muons rain down on the surface of the Earth continuously, passing through rock, concrete, metal, and virtually every other material with a penetrating power that makes X-rays look feeble by comparison. When muons pass through solid stone, some of them are absorbed or deflected. When they pass through empty space, they pass through unimpeded. By placing muon detectors at strategic positions around the base and inside the lower chambers of the Great Pyramid, the physicists could map the density of the pyramid's interior, identifying areas where the stone was solid and areas where the muon flux was unexpectedly high, indicating the presence of a void, an empty space where the pyramid's builders had, for reasons that remain unknown, left a gap in the otherwise continuous mass of limestone. The discovery electrified the world of archaeology and the world of physics simultaneously, because it demonstrated something that both disciplines had long suspected but had never been able to prove, that the most famous building on Earth, a building that has been explored, measured, mapped, photographed, scanned, and analysed by every generation of scholars since Napoleon's expedition to Egypt in 1798, still contains secrets that 2 centuries of the most intensive archaeological investigation in history have failed to uncover. The Great Pyramid is not fully known. Its interior is not fully mapped. The assumption that held for more than 100 years, the comfortable assumption that every chamber, every passage, every architectural feature of the pyramid had been discovered and documented, and that the only remaining questions were questions of interpretation rather than questions of discovery, was wrong. There is something inside the Great Pyramid that we have never seen, that we cannot currently reach without drilling through meters of solid limestone, that we do not understand, and that has been waiting in the darkness, sealed in stone, untouched by light or air or human presence, for 45 centuries, while generation after generation of explorers walked through the chambers below it without suspecting that an unknown space existed above their heads. By the end of tonight, you are going to understand how the hidden void was discovered, what it might be, why it matters, and what it tells us about the limits of human knowledge, even when the object of that knowledge is the most intensively studied structure in the history of the world. You are going to follow the muons from the upper atmosphere through the limestone blocks into the interior of the pyramid, and you are going to see how a technique borrowed from particle physics revealed something that centuries of archaeological exploration had missed. You are going to meet the scientists who conceived the project, the detectors they built, and the controversy that erupted when their results were published. And you are going to confront a question that the discovery poses with unsettling and exhilarating directness. If the Great Pyramid, the building we thought we knew better than any other ancient structure on the face of the earth, a building that has been probed and prodded and scanned and analysed for more than 200 years by the best minds and the best instruments that human civilization has produced, can still surprise us with a hidden void the size of a commercial airliner. What else is hidden inside the monuments of the past that we have not yet developed the means to see? Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now let us begin. To understand why the discovery of a hidden void inside the Great Pyramid matters, you must first understand what was already known about the pyramid's interior, how that knowledge was acquired, and why the assumption that the interior was fully mapped had become so deeply entrenched in Egyptological thinking that the discovery of an unknown space came as a genuine shock to the scholarly community. The history of exploring the Great Pyramid's interior is one of the longest and most dramatic stories in the history of archaeology, a story that stretches back more than 1,000 years, and that involves caliphs, treasure hunters, dynamite, robots, and ultimately subatomic particles. The Great Pyramid of Khufu was built around 2560 BC, according to the conventional chronology, during the reign of the second king of the 4th dynasty. It is the largest of the 3 pyramids on the Giza Plateau and the largest pyramid ever built in Egypt, with an original base length of approximately 230 meters on each side and an original height of approximately 146 meters. The pyramid contains an estimated 2.3 million blocks of limestone, each weighing on average 2.5 tons, with some of the largest blocks in the interior weighing as much as 80 tons. The precision of the construction is extraordinary. The base is level to within roughly 2 centimeters across its entire 230-meter length, and the sides are aligned to the cardinal points of the compass with an accuracy that modern surveyors have difficulty matching with contemporary instruments. The internal structure of the pyramid, as it was understood before the 2017 discovery, consists of 3 main chambers connected by a system of passages that are unique in the history of Egyptian pyramid construction. The lowest chamber, called the subterranean chamber, is cut into the bedrock beneath the pyramid and is reached by a descending passage that enters the pyramid on its northern face. The subterranean chamber appears to be unfinished, with a rough, irregular, deeply excavated floor and walls that still show the marks of the quarryman's copper and stone tools, and it may represent an abandoned plan for the king's burial chamber. Above it, reached by an ascending passage that branches off from the descending passage at a point roughly 28 meters inside the pyramid, is the so-called Queen's Chamber, a room with a gabled ceiling and a niche in its eastern wall that has been the subject of centuries of speculation. Despite its name, the Queen's Chamber was almost certainly not intended for a queen's burial. The name was applied by Arab visitors who noted the niche and assumed it was designed for a female burial following the convention of Islamic burial practice. The true purpose of the Queen's Chamber remains uncertain, with theories ranging from a serdab, a sealed room containing a statue of the king, to a storage chamber for funerary equipment, to an abandoned second burial chamber that was superseded by the King's Chamber above. The King's Chamber is reached by the Grand Gallery, one of the most remarkable interior spaces in any ancient building. The Grand Gallery is a steeply inclined passage, roughly 47 meters long and approximately 8.5 meters high, with walls that corbel inward in 7 steps as they rise, creating a soaring, tunnel-like space that narrows from roughly 2 meters at the base to roughly 1 meter at the ceiling. The corbelling technique, in which each course of stone projects slightly inward from the one below, is the same technique that Sneveru's builders used in the Red Pyramid at Dashur, and its application in the Grand Gallery represents the most ambitious and most successful use of corbelling in the entire history of Egyptian architecture. The Grand Gallery leads upward to the King's Chamber, a rectangular room approximately 10.5 meters long, 5 meters wide, and 6 meters high, lined entirely with polished granite and roofed with 9 massive granite beams, each weighing between 25 and 80 tons. Above the king's chamber are 5 relieving chambers, stacked one above the other in a configuration that is unique in Egyptian pyramid construction, designed to distribute the enormous weight of the pyramid above the burial chamber and to prevent the granite ceiling beams from cracking under the load. The relieving chambers are among the most remarkable structural features of the Great Pyramid, a 5-layered sandwich of granite beams and limestone blocks that collectively absorb and redistribute tens of thousands of tons of downward force, and that have maintained the structural integrity of the king's chamber for more than 4.5 millennia. The lowest 4 relieving chambers have flat roofs and floors formed by pairs of granite beams that span the width of the chamber. The uppermost relieving chamber has a gabled roof of massive limestone blocks that forms the final structural element in the protection system. The relieving chambers were unknown until Vyse blasted his way into them in 1837, and their discovery was a reminder that the Great Pyramid's interior was more complex and more architecturally sophisticated than anyone had previously imagined. It was also a precedent, a demonstration that the pyramid contained structural elements that were not visible from the known passages and chambers, and that could only be discovered by penetrating the limestone mass that concealed them. The first known penetration of the pyramid's interior after the original ceiling occurred in the 9th century AD, when the Abbasid Caliph al-Ma'mun, the son of Harun al-Rashid of the 1001 Nights, ordered his workers to bore a tunnel into the northern face of the pyramid in search of the treasure that was rumoured to be hidden inside. Al-Ma'mun was a patron of learning and science, the founder of the House of Wisdom in Baghdad, and his interest in the pyramid was driven as much by intellectual curiosity as by greed. His workers drove a tunnel through the limestone blocks, using chisels and fire, heating the stone with bonfires, and then dousing it with vinegar to cause it to crack, a method that was effective, but that left a ragged, irregular passage through the pyramid's mass that is still visible today as a gaping hole in the northern face, a permanent scar from the first time modern curiosity forced its way into the ancient structure. The tunnel eventually intersected the descending passage, and Al-Ma'mun's workers were able to access the interior chamber system for the first time in centuries. According to medieval Arab accounts, they found the chambers empty, their contents having been removed by tomb robbers in antiquity, though some accounts mention the discovery of a stone sarcophagus in the king's chamber, which remains there to this day, an empty, lidless box of red granite that is too large to have been removed through the existing passages, and that must therefore have been placed in the chamber before the pyramid was completed around it. The modern era of scientific exploration of the Great Pyramid began in the early 19th century, when the French scholars who accompanied Napoleon's invasion of Egypt in 1798 conducted the first systematic surveys of the Giza Plateau. The Description de l'Egypte, the massive multi-volume publication that resulted from the French expedition, included detailed plans and cross-sections of the Great Pyramid that established the basic framework for all subsequent study. But the most consequential early explorer was the British Army officer Howard Vyse, who conducted aggressive excavations at Giza in 1837 and 1838, using dynamite and iron rods to bore into the fabric of the pyramid in search of new chambers. Vyse's methods were destructive and would be considered unacceptable by modern archaeological standards, but his work produced one of the most important discoveries in the history of pyramid studies: the relieving chambers above the king's chamber. Vyse blasted his way into 4 previously unknown chambers stacked above the king's chamber, chambers that contained the only known inscriptions inside the Great Pyramid, quarry marks and team names painted on the rough surfaces of the blocks in red ochre by the original construction workers. The inscriptions include cartouches that spell the name Khufu, providing the most direct evidence linking the pyramid to the king who built it. In 1872, a British engineer named Wayneman Dixon, working inside the Queen's chamber with a local assistant, noticed a crack in the southern wall of the chamber and, probing it with a wire, discovered that it concealed the entrance to a narrow shaft approximately 20 centimeters square that penetrated the pyramid's masonry at an upward angle. Further investigation revealed a matching shaft in the northern wall. These two narrow shafts, which have come to be known as the Dixon shafts, penetrate the pyramid's mass at an upward angle and had been sealed behind the original wall surface, invisible from inside the chamber, since the day the pyramid was completed. Similar shafts had already been known in the king's chamber, where they extend from the north and south walls of the chamber all the way through the body of the pyramid to the exterior surface, and they have traditionally been interpreted as ventilation shafts, star shafts designed to align the king's spirit with specific stars in the night sky, or ritual passages intended to allow the king's spirit to travel between the burial chamber and the cosmos. The queen's chamber shafts, however, do not reach the exterior of the pyramid. They terminate inside the pyramid's masonry, blocked by limestone plugs that were revealed in 1993 by a small robot named Upuaut, designed by the German engineer Rudolf Gantenbrink, that was sent crawling up the shafts with a miniature camera. Gantenbrink's robot revealed that the southern shaft of the Queen's chamber was blocked by a small limestone slab fitted with two corroded copper pins, a discovery that generated enormous public excitement and intense scholarly debate about what might lie behind the blocking stone. In 2002, a follow-up robot mission, broadcast live on international television, drilled through the blocking stone and inserted a camera into the space behind it, revealing a second blocking stone a few centimeters further along the shaft. The anticlimax was palpable. The world had watched, hoping for a hidden chamber, and had found another wall. A subsequent mission in 2011, using a more advanced robot called Jedi, inserted a camera through the second blocking stone and revealed a small, rough-hewn chamber no larger than a closet, its walls bearing what appeared to be red ochre marks, possibly hieratic numerals or construction marks, that have never been definitively deciphered. The shafts of the Queen's chamber remain one of the enduring mysteries of the Great Pyramid, architectural features whose purpose is not understood and whose design, with their sealed and blocked terminations, seems deliberately enigmatic. It was against this background of partial knowledge and persistent mystery that the ScanPyramids project was launched in 2015. The project was an international collaboration led by the HIP Institute, the Heritage Innovation Preservation Institute, based in Paris, in partnership with the Faculty of Engineering at Cairo University and the Egyptian Ministry of Antiquities. The project's ambition was to apply the most advanced modern non-invasive scanning technologies available, including infrared tomography for detecting temperature anomalies in the pyramid's surface, muon tomography for imaging the density of the pyramid's interior, and three-dimensional photogrammetry for creating detailed surface models to the major pyramids of the 4th dynasty, including the Great Pyramid of Khufu, the Pyramid of Khafre, the Bent Pyramid at Darsha, and the Red Pyramid at Darsha, in order to detect previously unknown internal structures without drilling a single hole or removing a single stone. The project was explicitly designed as a non-invasive investigation, a way of seeing inside the pyramids without damaging them, using technologies that had never been applied to ancient monuments on this scale before. The key technology was muon tomography. Muons are subatomic particles created when high-energy cosmic rays, protons, and atomic nuclei traveling at near the speed of light through interstellar space collide with the atoms of the Earth's upper atmosphere. The collisions produce showers of secondary particles, including muons, which rain down on the surface of the Earth at a rate of roughly 10,000 per square meter per minute. Muons have a mass roughly 200 times that of an electron, and they carry enough energy to penetrate hundreds of meters of solid rock before being absorbed or deflected. This penetrating power makes them ideal probes for imaging the interiors of large, dense structures that are opaque to other forms of radiation. The principle of muon tomography is straightforward. Place a detector below or beside a structure and count the muons that pass through it. Where the structure is solid, fewer muons reach the detector because more of them are absorbed by the dense material. Where the structure contains a void, more muons reach the detector because they pass through empty space without being absorbed. The difference in muon flux between solid areas and void areas produces a density map of the structure's interior that can reveal hidden chambers, passages, and architectural features that are invisible from the outside. The use of muon tomography to study ancient structures was not in fact new. The technique had been pioneered in 1968 by the American physicist Luis Alvarez, who won the Nobel Prize in Physics that same year for his work on particle detectors. Alvarez placed a muon detector, called a spark chamber, in the Belzoni chamber beneath the second pyramid of Khafre at Giza, a chamber named after the Italian strongman and explorer Giovanni Battista Belzoni, who had first entered the pyramid in 1818 and used it to search for hidden chambers in the pyramid's upper mass. His results, published in the journal Science in 1970, showed no evidence of unknown voids, confirming that the second pyramid's upper structure was solid, or at least that any voids it contained were too small to be detected by the technology available at the time. Alvarez's experiment was a proof of concept, a demonstration that muon tomography could work in principle, but the detectors of the 1960s were crude by modern standards, with limited spatial resolution and long exposure times that made it difficult to detect anything smaller than a very large chamber. The ScanPyramids project deployed muon detection technology that was, in every respect, vastly more sophisticated than anything Alvarez had available. The project used 3 independent muon detection systems, each based on a different physical principle, each operated by a different team of physicists, and each positioned at a different location relative to the pyramid. The first system, developed by a team from Nagoya University in Japan, led by the physicist Kunihiro Morishima, used nuclear emulsion films, a technique that records the passage of individual muons as microscopic tracks in a photographic emulsion. The emulsion films were placed in the Queen's chamber of the pyramid, where they accumulated muon data over a period of several months, producing an image of the pyramid's interior that revealed density variations with a spatial resolution of a few centimeters. The second system, developed by a team from Keck, the high-energy accelerator research organization in Tsukuba, Japan, used scintillatoscopes, electronic detectors that record the position and direction of each muon as it passes through the detector. The hodoscopes were also placed inside the pyramid in the descending passage, providing an independent dataset that could be compared with the Nagoya results. The third system, developed by a team from CEA, the French Atomic Energy Commission, used large gas detectors that were placed outside the pyramid, on its northern face, where they collected muons that had passed through the entire thickness of the pyramid's mass from south to north. The use of 3 independent detection systems was a deliberate methodological choice, designed to ensure that any discovery would be robust and reproducible. If all 3 systems detected the same anomaly in the same location with the same approximate dimensions, the probability that the anomaly was a genuine feature of the pyramid's interior rather than a statistical artifact or an instrument error would be extremely high. The redundancy was essential because the stakes were enormous. A claim to have discovered a new void inside the Great Pyramid would attract intense scrutiny from both the archaeological and the physics communities, and any flaw in the methodology, any ambiguity in the data, any possibility of alternative explanation would be immediately and aggressively exploited by skeptics. The ScanPyramids team knew that their results would be subjected to the most rigorous scrutiny that the scientific community could provide, and they designed their experimental protocol accordingly. The data collection took months. The nuclear emulsion films, once exposed, had to be transported to Nagoya for chemical development and microscopic analysis, a process that required weeks of painstaking laboratory work to extract the muon tracks from the background noise. The electronic detectors generated streams of digital data that had to be processed through complex algorithms to reconstruct the trajectories of individual muons and to build up the density map of the pyramid's interior. The analysis was slow, meticulous, and technically demanding. And when the results began to emerge, they showed something that none of the researchers had expected. All 3 detector systems, independently and using different physical principles, detected a large void in the pyramid's mass located above the Grand Gallery, oriented in roughly the same direction as the Grand Gallery, and extending for a length of roughly 30 meters. The void was not a known feature of the pyramid. It did not correspond to any chamber, passage, or architectural element that had been documented by any previous explorer. It was, by every available measure, a genuinely new discovery, a feature of the pyramid's interior that had been sealed inside the monument since the day of its construction, and that had remained undetected for more than 4,500 years, despite 2 centuries of intensive archaeological investigation. The paper announcing the discovery was published in the journal Nature on the 2nd of November 2017, under the title Discovery of a Big Void in Khufu's Pyramid by Observation of Cosmic Ray Muons. The lead author was Kunihiro Morishima of Nagoya University, and the author list included physicists and Egyptologists from Japan, France, and Egypt. The paper was careful, measured, and deliberately conservative in its claims, a product of the scientific culture of understatement that characterizes publications in Nature, where extravagant assertions are discouraged and where the evidence is expected to speak for itself. It described the void as a large internal structure, using language that was intentionally neutral and that avoided the archaeologically loaded term chamber, and noted that its precise nature, whether it was a single large space, a series of smaller connected spaces, a horizontal passage, an inclined gallery parallel to the Grand Gallery below, or some other architectural configuration entirely, could not be determined from the muon data alone. The muon tomography technique can detect the presence and the approximate dimensions of a void, but it cannot determine the void's shape with precision, cannot reveal its contents, and cannot establish whether the void is a deliberately constructed space with a specific purpose or a byproduct of the construction process with no significance beyond the structural mechanics of pyramid building. The paper did not speculate about the void's purpose or its possible contents. It simply reported what the data showed, that there was a void, that it was large, roughly the same length as the Grand Gallery, and comparable in cross-section, and that it was real, confirmed independently by 3 different detection systems, using 3 different physical principles, operated by 3 different teams of physicists in 3 different countries. The convergence of the 3 data sets was the strongest evidence the researchers could offer that their discovery was genuine, and it was evidence that the scientific community found, after extensive review and debate, to be convincing. The reaction to the Nature paper was immediate and intense, and it revealed the deep fault lines that run through the world of Egyptian archaeology between the traditional archaeological establishment and the newer, technology-driven approaches that the ScanPyramids project represented. The former Egyptian Minister of Antiquities, Zahi Hawass, who had been one of the most prominent and most politically powerful figures in Egyptian archaeology for decades, was openly skeptical of the results. Hawass convened a committee of experts to review the findings and issued a statement questioning whether the muon data was sufficient to support the claim of a previously unknown void, arguing that the anomaly detected by the physicists might represent a structural feature of the pyramid's construction, such as a gap between courses of stone or a zone of reduced density within the pyramid's mass created by the loose rubble fill that was used in some areas of the pyramid's core, rather than a deliberately constructed chamber or passage. Hawass's skepticism was not mere obstructionism. It reflected a legitimate concern within the archaeological community that the physicists, however skilled in particle detection, might not fully appreciate the complexity of the pyramid's construction and might be interpreting as a void what was, in fact, a known or predictable feature of the building's fabric. Other Egyptologists were more receptive. The British archaeologist Mark Lehner, one of the foremost authorities on the Giza pyramids and the director of the Giza Plateau Mapping Project, acknowledged the significance of the muon data while cautioning against premature interpretation. Lehner noted that the Great Pyramid's internal structure is more complex than most people realize, with numerous gaps, crevices, and zones of reduced density that are inherent features of its construction method rather than deliberately created voids. The challenge, Lena suggested, was to determine whether the ScanPyramids void was a void in the conventional sense, a deliberately constructed space with a specific architectural or theological purpose, or whether it was a void in the purely physical sense, a zone of reduced density that might have no significance beyond the mechanics of pyramid construction. The French architect Jean-Pierre Houdet, who had been developing a theory about the construction of the Great Pyramid for more than a decade before the ScanPyramids discovery, saw the void as potential confirmation of his hypothesis. Houdin had proposed that the Great Pyramid was built using an internal ramp, a spiral ramp concealed within the body of the pyramid that allowed the construction workers to transport blocks to the upper levels without the need for an enormous external ramp that would have been visible from outside. Houdin's internal ramp theory predicted the existence of voids within the pyramid's mass, spaces left behind by the ramp structure after the construction was completed, and he argued that the ScanPyramids void corresponded to a section of his proposed internal ramp. Other scholars proposed alternative explanations. The void might be a counterweight chamber, a structural feature designed to balance the stresses created by the grand gallery below. It might be a construction gallery, a passage used during the building of the pyramid and then sealed when it was no longer needed. It might be a passage leading to an as-yet undiscovered chamber, or it might be something that no one has thought of, a feature of pyramid architecture that has no name because no one has ever seen anything like it before. The 2023 follow-up discovery added another dimension to the mystery, a smaller void detected by the ScanPyramids project behind the chevron stones on the north face of the pyramid was confirmed visually in March of 2023 when researchers inserted a small endoscopic camera through a gap between the stones and obtained the first visual images of the interior of a previously unknown space inside the Great Pyramid. The images showed a corridor-like space, roughly 9 meters long and approximately 2 meters wide, with a gabled ceiling formed by the massive chevron blocks that are visible from outside the pyramid. The corridor did not lead to a larger chamber, at least not visibly, and its purpose remains unknown, but its visual confirmation demonstrated that the muon tomography technique was capable of detecting real architectural features inside the pyramid with remarkable accuracy. The muons had predicted the corridor. The camera confirmed it. The technique worked. The confirmation of the north face corridor transformed the scholarly debate about the larger void above the Grand Gallery. If the muon data had been accurate about the corridor, it was likely to be accurate about the larger void as well. The question was no longer whether the void existed, but what it was, what it meant, and whether it could ever be accessed without damaging the pyramid's fabric. And this question, the question of what lies inside a sealed space at the heart of the most famous building on Earth, is the question that makes the ScanPyramids discovery one of the most consequential moments in the history of Egyptology and one of the most tantalizing unsolved mysteries in the entire history of human exploration. The core problem of the ScanPyramids discovery is not the void itself. It is the impossibility, at present, of determining what the void is. The muon data tells us that the void exists. It tells us approximately where it is, above the Grand Gallery, oriented in roughly the same direction. It tells us approximately how large it is, roughly 30 meters long, comparable in cross-sectional area to the Grand Gallery below. But it does not tell us what the void looks like from the inside, whether it has smooth walls or rough walls, whether it has a flat ceiling or a corbelled ceiling, whether it contains artifacts or inscriptions, or the remains of funerary equipment, or nothing at all. The void is, at present, a negative space, an absence of density in the muon data, a shadow in the particle flux that tells us something is missing, but cannot tell us what has taken its place. The scholarly debate about the nature of the void has crystallized around several competing hypotheses, each of which is consistent with the available data, and none of which can be confirmed or excluded without additional information that the current technology cannot provide. The hypotheses range from the structurally mundane to the archaeologically spectacular, and the gap between the most conservative and the most ambitious interpretations is a measure of how little we actually know about the internal architecture of the most famous building on Earth. The most conservative hypothesis, favoured by several structural engineers and by some Egyptologists who are skeptical of the discovery's archaeological significance, is that the void is a construction feature, a gap in the pyramid's fabric that was created during the building process, and that has no architectural or theological significance. According to this interpretation, the void may be a relieving space, similar in function to the 5 relieving chambers above the king's chamber, designed to reduce the weight of the pyramid's mass above the Grand Gallery and to prevent the Grand Gallery's corbelled walls from being crushed by the enormous load above them. The Grand Gallery is one of the most structurally ambitious spaces inside the pyramid, a steeply inclined corridor nearly 9 meters high and nearly 50 meters long, and the weight of the limestone above it is immense. A relieving void above the Grand Gallery would be an architecturally logical feature, a structural precaution that the builders incorporated into the design to protect the most vulnerable element of the pyramid's internal structure. But here is the problem with the relieving space hypothesis. The relieving chambers above the king's chamber are flat, horizontal spaces formed by pairs of massive granite beams that span the width of the chamber. They are structural elements whose form follows directly from their function. The ScanPyramids void, as far as the muon data can determine, is not a flat, horizontal space. It appears to be inclined, oriented at roughly the same angle as the Grand Gallery below, which rises at an angle of approximately 26 degrees from the horizontal. An inclined void is not a typical relieving space. Relieving spaces in Egyptian architecture are horizontal because their function is to distribute weight evenly across a horizontal plane. An inclined void would distribute weight unevenly, concentrating stress at the lower end and reducing it at the upper end, which is the opposite of what a relieving structure is designed to do. The inclination of the void, if confirmed by future investigation, would argue against the relieving space interpretation and would suggest that the void has a different purpose, one that is not explained by structural engineering alone. The second hypothesis, which has attracted considerable attention from both scholars and the general public, is that the void is a previously unknown passage or gallery, a deliberately constructed corridor that was built into the pyramid for a specific and as yet unknown purpose, and then sealed and concealed when that purpose was fulfilled, or when the construction of the pyramid rendered further access unnecessary. Several variations of this hypothesis have been proposed. Jean-Pierre Hodan's internal ramp theory, which proposes that the pyramid was constructed using a spiral ramp concealed within the body of the pyramid, predicts the existence of inclined passages within the pyramid's mass that correspond to sections of the ramp. If the ScanPyramids void is a section of Houdin's proposed internal ramp, its inclined orientation would be explained, and its discovery would provide powerful evidence for a theory of pyramid construction that has been debated for more than a decade without conclusive verification. Other scholars have proposed that the void might be a construction gallery, a passage used by the workers who built the Grand Gallery and the King's Chamber to transport materials and equipment to the upper levels of the pyramid and then sealed after the construction was complete. A construction gallery would explain the void's inclined orientation, its close proximity to the Grand Gallery, and its approximate dimensions, which are consistent with a passage wide enough and tall enough to allow workers to move materials and equipment through the pyramid's interior during the years of active construction, and it would be consistent with the general principle that the pyramid's builders used temporary internal passages during construction that were sealed and concealed in the finished monument. The chamber hypothesis is the most spectacular and the most publicly exciting, and it is also the most controversial and the most difficult to evaluate against the currently available evidence. It proposes that the void is a previously unknown chamber, a room that was deliberately designed and constructed as an integral part of the pyramid's original architectural program, and that may contain objects, inscriptions, or architectural features that have been sealed in complete darkness and total isolation for more than 4,500 years. The chamber hypothesis is the one that generates the most public excitement, because it raises the possibility, however remote, that the Great Pyramid contains a space that no one has entered since the day it was sealed, a time capsule of the 4th dynasty that might contain evidence of the king, his burial, his funerary equipment, or the construction process that would transform our understanding of the pyramid and of the civilization that built it. The chamber hypothesis is also the most difficult to evaluate, because the evidence that would confirm or deny it, the visual and physical evidence of the void's interior, is currently inaccessible. The void is located deep within the pyramid's mass, surrounded on all sides by meters of solid limestone, and there is no known passage that connects it to any part of the pyramid's existing chamber system. Reaching the void would require either drilling through the limestone, an invasive procedure that would damage the pyramid's fabric, and that has been firmly opposed by the Egyptian authorities, or developing a new non-invasive technology capable of imaging the void's interior with sufficient resolution to determine its shape, its contents, and its architectural character. Neither option is currently available. Drilling is politically and ethically unacceptable. The imaging technology does not yet exist, and so the void remains sealed, its nature unknown, its contents a matter of speculation rather than evidence, a mystery that is all the more tantalizing because the means of solving it are, for the moment, beyond our reach. And it gets stranger. The ScanPyramids void is not the only anomaly detected by the project's instruments. The infrared thermography surveys conducted during the early phases of the project, in which the pyramid's surface was scanned with thermal cameras to detect temperature anomalies that might indicate the presence of internal voids or passages, revealed an area on the eastern face of the pyramid, near the base, where the surface temperature was significantly different from the surrounding stone. The thermal anomaly suggested the presence of a cavity or a passage behind the surface, a space where the air circulation differed from the dense, thermally uniform mass of the pyramid's core. The thermal anomaly has not been fully explained, and its relationship to the muon-detected void, if any, is unknown. The Great Pyramid, it appears, may contain not one but multiple unknown features, each one detected by a different instrument, each one consistent with a different kind of internal space, and each one currently beyond the reach of any technology that could determine its nature. The ethics of investigating the void have become a major topic of debate within the archaeological community, and the debate illuminates a fundamental tension in the modern practice of archaeology between the desire to know and the obligation to protect. The Great Pyramid is not merely an archaeological site. It is one of the most important cultural heritage monuments on Earth, the last surviving wonder of the ancient world, a structure of incalculable historical, cultural, and symbolic value. Any intervention that damages the pyramid, even an intervention motivated by the most legitimate scientific curiosity, diminishes the monument in a way that cannot be reversed. A drill hole, once made, cannot be unmade. A stone, once removed, cannot be restored to its original position with the same precision that the original builders achieved. The integrity of the pyramid is a finite resource that is consumed by every invasive investigation, and the archaeological community has a responsibility to ensure that the resource is not consumed faster than the information it yields is worth. But the desire to know is powerful, and the ScanPyramids void tests the limits of that restraint more severely than any previous discovery. Here is a void, 30 meters long, sealed inside the most famous building on Earth, detected by 3 independent instruments, confirmed by the most rigorous scientific methodology available, and utterly, completely, maddeningly inaccessible. We know it is there. We cannot see it. We cannot reach it. We cannot determine what it is. And we are faced with a choice that has no easy answer. Do we wait for technology to develop a non-invasive means of imaging the void's interior, a process that might take years or decades? Or do we intervene, carefully and minimally, to obtain the visual evidence that would resolve the mystery? Something is wrong with our assumptions about how completely we can know the past. The Great Pyramid has been explored for more than 200 years. Every passage has been walked. Every chamber has been measured. Every surface has been photographed. Every block has been catalogued. The pyramid has been surveyed with laser scanners, modelled with photogrammetry, analysed with X-ray fluorescence, and probed with ground-penetrating radar. It is the most thoroughly investigated structure in the history of archaeology, and it still has secrets. The muon data proved it. The void is there. We did not know about it. We could not have known about it without the muon detectors. And the question that this raises, the question that should unsettle every archaeologist and every historian who has ever assumed that the major monuments of the ancient world have been fully explored and fully understood, is, what else do we not know? But here is what makes this truly terrifying. The Great Pyramid is the best case. It is the most studied, the most measured, the most photographed, the most analysed ancient structure on the planet. If the Great Pyramid contains a void that went undetected for 2 centuries of intensive investigation, what might be hidden inside the structures that have not been investigated with the same thoroughness? What might be concealed within the pyramids of Darsha, or Abusir, or Meidum, or the dozens of other pyramids in the Nile Valley that have never been scanned with muon detectors? What might be sealed inside the temples of Karnak, the tombs of the Valley of the Kings, the palaces of Knossos, the ziggurats of Mesopotamia, the pyramids of Meroe? The ScanPyramids discovery does not merely tell us that the Great Pyramid has a hidden void. It tells us that the archaeological record is deeper and more complex and more poorly understood than we assumed, that the things we have found are a fraction of the things that remain to be found, and that the technologies we have been using to explore the past have been, until very recently, inadequate to the task of revealing what the past still conceals. The void inside the Great Pyramid is a metaphor, whether the builders intended it as one or not. It is a physical embodiment of the gap between what we know and what we think we know, between the map we have drawn and the territory it is supposed to represent, between the confidence we feel in our understanding of the ancient world and the actual completeness of that understanding. We drew the map. We said the map was complete. We were wrong. There was always more territory. There was always a void that the map did not show. And the void, now that it has been detected, forces us to redraw the map, to acknowledge the blank spaces, and to accept that the most carefully studied monument on Earth still has the power to remind us of how much we do not know. The implications extend beyond the Great Pyramid to the entire practice of archaeology. If muon tomography can reveal a 30-meter void inside the most thoroughly investigated structure in the world, what might it reveal inside structures that have been investigated far less thoroughly? The technique has already been applied to volcanoes, to nuclear reactors, to customs inspection of shipping containers, and to the inspection of damaged buildings after earthquakes. Its application to archaeology is still in its infancy. The ScanPyramids project was the first large-scale deployment of muon tomography at an archaeological site, and the results have demonstrated that the technique has the potential to revolutionize the field by revealing internal features of ancient structures that cannot be detected by any other means. The pyramids of the Nile Valley, the temples of Greece and Rome, the cathedrals of medieval Europe, the stepped pyramids of Mesoamerica, any structure that is large enough and dense enough to produce a measurable attenuation of the muon flux could, in principle, be scanned using the same technique that revealed the void inside the Great Pyramid. The technology exists. The cosmos provides the muons. The only question is whether the archaeological community has the resources, the institutional will, and the intellectual courage to apply the technology on the scale that the archaeological record demands. The silence of the void is the kind of silence that makes you listen harder. It is not the silence of emptiness. It is the silence of a presence that has not yet been identified, a shape that has not yet been seen, a meaning that has not yet been decoded. The void has been there for more than 4,500 years. It has been surrounded by millions of tons of limestone. It has been sealed against light, against air, against moisture, against every force of deterioration that has consumed the surfaces of the pyramid's exterior. Whatever is inside the void, whether it is empty air or something more, is in a state of preservation that no surface exposure could match. The darkness has been absolute. The temperature has been constant. The humidity has been controlled by the thermal mass of the surrounding stone. The void is, in every sense, a sealed environment, a capsule of the Fourth Dynasty that has been maintained in conditions that any modern conservator would envy, and it is waiting, in the darkness, for the light. The muon tomography technique itself deserves closer examination, because the way the discovery was made is as significant as the discovery itself. The technique works by exploiting a simple physical principle. Muons are absorbed by matter in proportion to the density and the thickness of the material they pass through. A muon traveling through solid limestone encounters more atoms, more opportunities for interaction, and more chances of being absorbed or deflected than a muon traveling through air. By counting the muons that arrive at a detector after passing through a structure, and by comparing that count with the number of muons that would be expected if the structure were uniformly solid, the physicist can identify areas where fewer muons were absorbed than expected, indicating the presence of less dense material or empty space. The elegance of the technique is that it requires no contact with the structure being imaged. The muons are provided free of charge by the cosmos. They fall continuously, day and night, rain or shine, penetrating the pyramid from every direction with a statistical regularity that makes them ideal for long exposure imaging. The detectors are passive devices that sit quietly and count, accumulating data over weeks and months until the statistical significance of any anomaly becomes unmistakable. The technique is patient in a way that matches the patience of the monument it is studying. The muons have been falling through the Great Pyramid since the day it was built. The only thing that has changed is that someone finally thought to count them. The Nagoya University team's nuclear emulsion films are worth examining in some detail because they represent one of the most elegant experimental techniques in modern physics applied to one of the oldest structures in human history. Nuclear emulsion is a photographic technique in which a thin layer of silver halide crystals is spread on a glass or plastic substrate. When a charged particle, such as a muon, passes through the emulsion, it ionizes the silver halide crystals along its path, leaving a latent track that can be developed and fixed by standard photographic chemistry, and then examined under a microscope. Each track records the passage of a single particle, and the direction of the track records the direction from which the particle arrived. By placing multiple emulsion films at known positions inside the pyramid and exposing them for months, the Nagoya team accumulated millions of individual muon tracks, each one a record of a single cosmic ray muon's passage through the pyramid's mass. The accumulated tracks, when analyzed statistically, produced a density map of the pyramid's interior with a spatial resolution of a few centimeters, sufficient to detect any void larger than a few meters in extent. The Cake team's scintillator hodoscopes used a different physical principle to achieve the same result. Scintillator detectors are made of transparent plastic that emits a tiny flash of light when a charged particle passes through it. The flash is detected by a photomultiplier tube, an electronic device that converts the light into an electrical signal that can be recorded by a computer. By arranging multiple layers of scintillator in a grid pattern, the hodoscope can determine both the position and the direction of each muon that passes through it, providing the same directional information as the nuclear emulsion, but in real time, with electronic rather than photographic recording. The hodoscopes were placed in the descending passage of the pyramid, a location that gave them a different viewing angle from the emulsion films in the Queen's chamber, and they accumulated data over a period of months, producing an independent density map that could be compared with the Nagoya results. The CEA team's gas detectors, placed outside the pyramid on its northern face, represented the third and most challenging of the three detection systems. Unlike the Nagoya and AK detectors, which were placed inside the pyramid where they could detect muons arriving from a limited range of directions, the CEA detectors had to detect muons that had passed through the entire thickness of the pyramid, a path length of more than 100 meters of solid limestone. The muon flux at this thickness is enormously attenuated, with only a tiny fraction of the incoming muons surviving the passage, and the detectors needed to be extremely sensitive and to accumulate data over a very long period to achieve the statistical significance needed to detect a void. The CEA gas detectors used a technology called micromegas, developed originally for particle physics experiments at CERN, that is capable of detecting individual muons with high efficiency and high spatial resolution. The use of this technology outside the pyramid in a field deployment that was far from the controlled laboratory environment for which the detectors were originally designed was itself a significant technical achievement that pushed the boundaries of what was possible with muon detection technology. The convergence of the three datasets was the decisive factor in the scientific community's acceptance of the discovery. Any one of the three detector systems, taken alone, might have been dismissed as an instrumental artifact, a statistical fluctuation, or a systematic error. But the probability that three independent systems, using three different physical principles, operated by three different teams, at three different locations, would all produce the same false result is vanishingly small. The void was real, the science was sound, and the Great Pyramid, the building that the world thought it knew, had revealed a secret that it had kept for 45 centuries. The discovery changed something fundamental about the way Egyptologists think about the pyramids, something that is difficult to articulate but that is felt by every scholar who has absorbed the implications of the muon data. Before the ScanPyramids discovery, the internal architecture of the Great Pyramid was considered a closed subject, a problem that had been solved, a map that had been completed. The chambers were known, the passages were known, the relieving chambers were known, the shafts were known. Every accessible space inside the pyramid had been entered, measured, photographed, and documented. The only remaining questions were questions of interpretation. Why were the chambers arranged as they were? What was the purpose of the shafts? Why was the subterranean chamber left unfinished? These were important questions, but they were questions about a known structure. Questions whose answers, when they came, would refine the existing understanding rather than overturning it. The ScanPyramids void overturned it. The internal architecture of the Great Pyramid is not fully known. There are features inside the pyramid that have never been documented, that were not predicted by any existing theory, and that cannot be explained by the current understanding of how the pyramid was designed and built. The comfortable assumption that the map was complete has been replaced by the unsettling realization that the map has a blank space in it, a region marked unknown, a void in the knowledge that mirrors the void in the stone. The paradigm has shifted, and the shift, once it has occurred, cannot be reversed. The Great Pyramid will never again be regarded as a fully known structure. It will always be a structure that contains a mystery, a building whose interior has not been fully explored, a monument that still has the capacity to surprise us, despite everything we have done to understand it. The 2023 discovery of the North Face corridor provided a crucial test of the muon tomography technique, and a tantalizing preview of what future investigations might reveal about the larger void. The corridor, located behind the massive chevron blocks that are visible on the pyramid's north face above the original entrance, had been predicted by the ScanPyramids muon data, and was confirmed when researchers inserted a 4mm diameter endoscopic camera through a narrow gap between the stones. The images captured by the camera showed a space roughly 9 meters long, approximately 2 meters wide, and roughly 2 meters high, with a gabled ceiling formed by the chevron blocks themselves. The walls were rough, unfinished limestone, showing the marks of the quarryman's tools, and the floor was covered with a fine layer of dust that had accumulated over millennia in the sealed, airless environment. The space contained no artifacts, no inscriptions, and no evidence of human activity beyond the act of construction itself. It was an empty room, a blank page, a silence made of stone. The emptiness of the North Face corridor was, paradoxically, one of the most significant aspects of the discovery. It demonstrated that the pyramid contains constructed spaces that were never used for burial, for storage, or for any other purpose that would leave a material trace. The corridor appears to be a structural feature, a space created by the arrangement of the chevron blocks that may have served a load-bearing function during construction, or that may have been intended to protect the original entrance passage below from the weight of the pyramid above. Its existence suggests that the pyramid's internal architecture includes a category of space that does not correspond to any known functional type. Spaces that are neither chambers nor passages nor shafts, but something else. Structural voids that were built into the pyramid's fabric for reasons that are related to the mechanics of construction rather than to the theology of burial. If the north face corridor is a structural feature rather than a functional space, it raises the possibility that the larger void above the Grand Gallery may also be a structural feature, a space that was created by the construction process, and that has no contents, no inscriptions, and no archaeological significance beyond its contribution to the structural integrity of the pyramid. This is the interpretation favoured by the conservative wing of the scholarly community, and it is the interpretation that would, if confirmed, represent the least dramatic resolution of the mystery. The void would be important as evidence of the pyramid's construction technique, but it would not be a hidden chamber, a sealed passage, or a repository of undiscovered treasures. It would be an empty space, architecturally interesting but archaeologically sterile. But the conservative interpretation does not easily account for the size and the orientation of the void. The north face corridor is 9 meters long, a relatively modest space that can be explained as a byproduct of the chevron block arrangement. The larger void is roughly 30 meters long, comparable in size to the Grand Gallery itself, and it appears to be inclined at a similar angle. A structural void of this size and this orientation is not easily explained by the mechanics of pyramid construction, and its resemblance to the Grand Gallery, in both dimensions and inclination, suggests a deliberate architectural parallel rather than an accidental byproduct. If the void is a deliberate construction, it was planned, designed, and incorporated into the pyramid's architecture for a specific purpose, and the question of what that purpose was becomes one of the most important unsolved problems in the study of the Great Pyramid. The American Egyptologist Bob Breyer, who has written extensively about the Great Pyramid and its mysteries, has described the ScanPyramids void as the most significant discovery inside the pyramid since Howard Weiss blasted his way into the relieving chambers in 1837. Breyer's comparison is apt, because the relieving chambers, like the ScanPyramids void, were spaces that were not predicted by any existing theory of the pyramid's design, and that were discovered only when technology, in Weiss's case dynamite, in the ScanPyramids case muon detectors, made it possible to see beyond the visible surfaces of the monument. The parallel suggests that the Great Pyramid's internal architecture may be significantly more complex than the current model indicates, that the known chambers and passages may represent only a fraction of the spaces that the builders incorporated into the pyramid's design, and that the full plan of the pyramid's interior may not be knowable until technologies are developed that can image every cubic meter of the monument's 2.3 million cubic meters of stone. The French physicist Sébastien Procureur, one of the principal investigators of the ScanPyramids project, and a specialist in muon detector technology, has spoken about the discovery with a mixture of scientific precision and personal wonder that captures the emotional dimension of the moment. Procureur described the first time the data from the CEA gas detectors showed the void as a moment of disbelief, followed by a mounting excitement that was tempered by the awareness that the claim would need to withstand the most rigorous possible scrutiny before it could be published. The scientific process, Procureur noted, requires patience, requires the suppression of excitement in favor of methodical verification, requires the willingness to consider every alternative explanation before accepting the most dramatic one. But when the verification was complete, when all 3 detector systems had confirmed the same result, when every alternative explanation had been considered and found wanting, the excitement returned, and with it the awareness that the team had found something that no one had seen for 4,500 years. Something that had been waiting in the darkness since before the Trojan War, since before the founding of Rome, since before the writing of the oldest books of the Hebrew Bible, sealed in stone, untouched by light or air, a secret that the pyramid had kept through every century of human history, and that it had finally, reluctantly, partially revealed. The silence of the void is the silence of a question without an answer. We know the void is there. We do not know what it is. We cannot reach it. We cannot image it. We cannot determine its purpose or its contents or its relationship to the other spaces inside the pyramid. The void exists in a liminal zone between knowledge and ignorance, between detection and understanding, between the particle physics that revealed its presence and the archaeology that cannot yet explain its meaning. It is the place where science delivered a fact and then stepped back, unable to provide the interpretation that would transform the fact into understanding. It is, in this profound and uncomfortable sense, the most honest expression of the current state of our knowledge about the Great Pyramid. We know more than anyone has ever known, and we understand less than we thought we did. The void is an invitation and a rebuke simultaneously, a reminder that the past still holds weights and a challenge to develop the means of revealing them. The ScanPyramids discovery did not emerge from a vacuum. It is part of a broader revolution in the application of physics technologies to archaeological problems, a revolution that has been building for decades and that the Great Pyramid void has brought to the attention of the global public in the most dramatic way possible. The history of this revolution and the specific technologies that have been deployed at archaeological sites around the world provides essential context for understanding what the void discovery means and what it portends for the future of the discipline. The first chapter of this revolution belongs to Luis Alvarez and his 1968 muon experiment at the Pyramid of Khafre. Alvarez was not an Egyptologist. He was a particle physicist, a Nobel laureate who had spent his career studying the fundamental particles that make up the universe. His interest in the pyramids was driven not by a fascination with ancient Egypt, but by a realization that the technology he used in his laboratory, the spark chambers and scintillation counters that detected the passage of subatomic particles, could be repurposed to image the interiors of large, dense structures that were opaque to conventional inspection methods. Alvarez's experiment at Khafre was a proof of concept. He placed his spark chamber in the lower chamber of the pyramid and collected muon data for several months. The results showed that the upper mass of the pyramid was uniformly dense, with no hidden chambers of significant size. The experiment was a success in the technical sense. It demonstrated that muon tomography could work at an archaeological site. But it was a disappointment in the archaeological sense, because it found nothing new. The importance of Alvarez's experiment was not the result, but the precedent. It demonstrated that the barrier between physics and archaeology could be crossed, that the tools of one discipline could be productively applied to the problems of another, and that the ancient world contained questions that could be answered not by digging, but by detecting. The lesson was slow to take hold. For decades after Alvarez's experiment, the archaeological community showed limited interest in muon tomography, partly because the technology was expensive and logistically demanding, partly because the 1968 experiment had failed to produce a dramatic discovery, and partly because the culture of archaeology, with its emphasis on fieldwork, excavation, and the physical handling of material evidence, was resistant to a technique that involved sitting passively beside a detector and waiting for subatomic particles to accumulate. The technology continued to develop, however, in fields far removed from archaeology. Muon tomography was applied to the inspection of volcanic structures, where it was used to image the internal magma chambers and conduit systems of active volcanoes in Japan, Italy, and Central America. The technique provided volcanologists with information about the distribution of magma and gas within a volcano that could not be obtained by any other means, and it contributed to the development of eruption prediction models that have saved lives in volcanic hazard zones around the world. The volcanic applications demonstrated that muon tomography could work at large scales, in harsh field conditions, and with structures that were far larger and far more irregularly shaped than the controlled geometries of laboratory experiments. Muon tomography was also applied to the inspection of nuclear reactors, where it was used to image the interiors of damaged reactor buildings without exposing workers to dangerous levels of radiation. After the Fukushima Daiichi nuclear disaster in Japan in 2011, muon detectors were deployed at the damaged reactor buildings to determine the location of the melted fuel, information that was essential for planning the decommissioning operation, but that could not be obtained by any other means because the radiation levels inside the buildings were too high for human entry or conventional inspection equipment. The Fukushima application demonstrated that muon tomography could provide critical information about the interior of structures that were physically inaccessible, a capability that would prove directly relevant to the investigation of sealed spaces inside the Great Pyramid. The application of muon tomography to customs inspection, specifically the detection of contraband nuclear material concealed inside shipping containers, provided another step in the technology's development. Researchers at Los Alamos National Laboratory in the United States developed muon scattering tomography, a variant of the technique that uses the deflection of muons rather than their absorption to image the contents of shipping containers. The technique can detect the presence of heavy elements, such as uranium or plutonium, inside containers without opening them, providing a non-invasive inspection capability that is impossible to defeat by shielding or concealment. The customs application demonstrated that muon tomography could be deployed in operational environments, with rapid data collection times and automated analysis, capabilities that would eventually be adapted for archaeological use. The history of discovering hidden spaces inside Egyptian pyramids extends far beyond the Great Pyramid, and provides an essential framework for understanding why the ScanPyramids void is both surprising and, in retrospect, entirely predictable. The Egyptian pyramids are not solid masses of stone. They are buildings, complex three-dimensional structures with internal chambers, passages, corridors, shafts, and structural features that were designed and built according to plans that we do not fully understand, and that varied significantly from one pyramid to the next. The assumption that the interior of any pyramid is fully known based on the chambers and passages that have been accessed through existing entrances is an assumption that the archaeological record has repeatedly proven to be wrong. The relieving chambers above the King's Chamber in the Great Pyramid, discovered by Weiss in 1837, are the most famous example of hidden spaces found inside a pyramid. But they are not the only example. The Pyramid of Amenemhat III at Dashur, excavated by Jacques de Morgan in the 1890s, contained a labyrinthine subterranean system of chambers, corridors, and blind passages that was far more complex than anything the excavators had anticipated. The Pyramid of Senusret II at Lahoun, excavated by Flinders Petrie in the 1880s, had its entrance not on the traditional northern face, but on the southern side, concealed beneath the pavement of the courtyard, a location so unexpected that Petrie spent months searching for it before finding it by accident. The Pyramid of Senusret III at Dashur contained a subterranean complex so elaborate that it took multiple excavation seasons to fully explore, with false passages, concealed shafts, and decoy chambers designed to mislead tomb robbers into believing they had found everything there was to find. The pattern is clear. Egyptian pyramid builders were masters of concealment. They hid entrances, they sealed passages, they created false chambers to misdirect intruders. They built structural features that were invisible from the exterior, and that could only be discovered by penetrating the pyramid's mass. The Great Pyramid, with its unique internal architecture and its unparalleled scale, would have been the ideal candidate for concealment of the highest order. If any pyramid in Egypt was likely to contain hidden spaces that had escaped detection by centuries of exploration, it was the Great Pyramid, because the Great Pyramid was built by the most skilled, the most resourceful, and the most architecturally ambitious builders in Egyptian history. And because the stakes of protecting the king's burial were never higher than they were for Khufu, the most powerful pharaoh of the most powerful dynasty in Egyptian history. The robot missions to the Queen's chamber shafts provide another case study in the discovery of hidden features inside the Great Pyramid, and they illustrate both the promise and the limitations of remote exploration technology. Rudolf Gantenbrink's Upu-Out robot, which explored the southern shaft of the Queen's Chamber in 1993, was a miniature tracked vehicle equipped with a camera, lights, and laser alignment instruments designed to crawl up the narrow shaft and transmit video images back to the operators at the shaft's entrance. The robot travelled approximately 65 meters up the shaft before encountering the blocking stone with its copper pins, a discovery that generated worldwide media attention and that raised, for the first time in the modern era, the possibility that the Great Pyramid might contain sealed spaces that had never been accessed. The 2002 follow-up mission, which drilled through the blocking stone on live television and found a second blocking stone behind it, demonstrated both the technical capability and the fundamental limitation of remote exploration inside the pyramid. The technology could deliver a camera to a location deep inside the pyramid's mass. It could not, however, determine what lay beyond the second blocking stone without further intervention, whether drilling or mechanical removal, risked damaging the very features that the exploration was designed to study. The dilemma was a preview of the dilemma that the ScanPyramids void would later present on a much larger scale. The technology can detect the presence of a hidden space, but it cannot reveal its contents without physical access, and physical access cannot be achieved without damaging the monument. The development of future technologies that might resolve this dilemma is one of the most active areas of research at the intersection of physics and archaeology. Several approaches are under investigation. Advanced muon detectors with higher spatial resolution and shorter exposure times could produce more detailed images of the void's shape and dimensions, potentially distinguishing between a single large space and a series of smaller connected spaces. Cosmic ray muon imaging with multiple detector positions, a technique called muon radiography, could produce three-dimensional tomographic images of the void that would reveal its cross-sectional shape at different points along its length. Miniaturized robotic systems, building on the technology developed for the Queen's Chamber shaft explorations, could potentially be inserted through narrow gaps in the stonework to deliver cameras and sensors to the vicinity of the void without drilling through solid blocks. And ultrasonic imaging, which uses high-frequency sound waves to map the internal structure of materials, could potentially be applied to the limestone blocks surrounding the void to determine whether any seams, joints, or passages connect the void to the existing chamber system. Each of these technologies has limitations, and none of them is currently capable of providing the definitive images of the void's interior that would be needed to resolve the scholarly debate about its nature and purpose. But the pace of technological development is rapid, and the ScanPyramids discovery has created a powerful incentive for the development of new non-invasive imaging technologies that could be applied not only to the Great Pyramid but to archaeological sites around the world. The void has become a catalyst for technological innovation, a challenge that is driving the development of tools that will benefit archaeology far beyond the specific case that inspired them. The Great Pyramid void is not the only hidden space that modern technology has revealed inside ancient structures, and the global parallels illuminate the broader significance of the ScanPyramids discovery in ways that the Egyptian case alone cannot provide. In Mesoamerica, a team of Mexican and international researchers used muon tomography to scan the Pyramid of the Sun at Teotihuacan in Mexico, one of the largest pyramids in the Americas, and detected anomalies in the pyramid's density distribution that suggested the presence of previously unknown internal features. The Teotihuacan scan was less conclusive than the ScanPyramids results, because the pyramid's construction, using layers of earth and rubble rather than solid stone, produces a more heterogeneous density distribution that is harder to interpret, but it demonstrated that the technique could be applied to New World monuments, and that the pyramids of the Americas, like those of Egypt, might contain hidden spaces that conventional excavation has not revealed. In Europe, ground-penetrating radar and electrical resistivity tomography, techniques that are less penetrating than muon tomography, but that are more widely available and less expensive to deploy, have been used to detect hidden features inside and beneath medieval cathedrals, Roman temples, and prehistoric monuments. The discovery of a buried henge monument at Durrington Walls near Stonehenge in England, detected by magnetometry survey in 2015, demonstrated that even the most intensively studied archaeological landscapes can contain major features that are invisible from the surface, and that can only be detected by geophysical survey. The buried henge, a massive circular enclosure roughly 500 meters in diameter, defined by a ring of more than 90 buried stones, had been completely unknown before the survey, despite more than a century of archaeological investigation in the Stonehenge landscape. The parallel with the ScanPyramids void is direct, a major structural feature hidden beneath a well-studied surface, undetected by conventional methods, revealed by technology. The discovery of the so-called boat chamber at the base of the Great Pyramid itself provides another instructive parallel. In 1954, the Egyptian archaeologist Kamal el-Malak discovered a sealed pit cut into the bedrock on the south side of the pyramid, covered by massive limestone slabs that weighed more than 15 tons each. When the slabs were removed, el-Malak found a disassembled cedar boat, more than 43 meters long, that had been sealed in the pit since the pyramid was built. The boat, now reconstructed and displayed in a museum beside the pyramid, is one of the most spectacular archaeological discoveries ever made in Egypt, and it was found not inside the pyramid but beside it, in a space that had been invisible from the surface, and that no one had suspected existed until the pit was accidentally exposed during a cleaning operation. A second boat pit, detected by drilling and by ground-penetrating radar, was excavated between 2011 and 2021 by a joint Japanese-Egyptian team, revealing another disassembled boat in a similar state of preservation. The boat pits demonstrate that the Great Pyramid complex contains sealed spaces that have survived intact for more than 4,500 years, spaces whose contents are in a state of preservation that is extraordinary by any standard, and spaces that were discovered not by planned investigation but by accident, by the lucky intersection of a routine operation with an unknown feature of the monument's design. The accumulating evidence from the Great Pyramid complex alone, the relieving chambers, the Queen's Chamber shafts, the boat pits, the north face corridor, and the large void, suggests that the monument's designers incorporated a far greater number of internal and external spaces into their plan than the traditional model of the pyramid's architecture accounts for. Each new discovery has expanded the known plan of the pyramid, adding features that were not predicted by any existing theory and that have required the revision of the architectural model to accommodate them. The pattern suggests that the plan is still incomplete, that there may be additional features, additional voids, additional sealed spaces that have not yet been detected, and that will require future generations of technology to reveal. The cross-disciplinary nature of the ScanPyramids discovery is itself one of its most significant aspects. The void was discovered not by archaeologists, but by physicists. The technology that detected it was developed not for archaeological purposes, but for particle physics research, for volcanic monitoring, for nuclear reactor inspection, and for customs enforcement. The intellectual breakthrough that made the discovery possible was not an advance in archaeological theory or method, but an advance in the application of fundamental physics to a problem that the archaeological community had not recognized as solvable. The discovery is a testament to the power of interdisciplinary collaboration, to the value of bringing together experts from different fields who see the same problem from different angles and who bring different tools, different assumptions, and different methodological traditions to the task of solving it. The French architect Mehdi Tayyoubi, the co-director of the ScanPyramids project and the founder of the HIP Institute, has spoken eloquently about the importance of this interdisciplinary approach. Tayyoubi is not a physicist, he is not an Egyptologist. He is an architect and a heritage preservation specialist who recognized that the technologies being developed in physics laboratories had the potential to transform the study of ancient monuments and who organized the institutional framework, the funding, the diplomatic relationships, and the logistical infrastructure needed to deploy those technologies at one of the most politically sensitive and most archaeologically important sites in the world. Tayyubi's contribution was not technical, it was organizational. He built the bridge between the physics laboratory and the archaeological site, and the void was discovered because that bridge existed. The lesson of the ScanPyramids project is that the greatest advances in the study of the past may come not from within the discipline of archaeology, but from outside it, from fields that possess technologies and methodologies that the archaeological community has not yet learned to use. The muon was discovered in 1936. The technique of muon tomography was demonstrated in 1955. Alvarez applied it to a pyramid in 1968. And the first major discovery using the technique at a pyramid, the ScanPyramids void, came in 2017, nearly half a century after Alvarez's proof of concept and more than 8 decades after the muon was first identified. The gap between the availability of the technology and its productive application to archaeology is a measure of the institutional and cultural barriers that separate disciplines, barriers that the ScanPyramids project managed to cross, but that continue to impede the application of advanced physics technologies to archaeological problems worldwide. The application of non-invasive scanning to other pyramids in the Nile Valley has already begun to produce results that suggest the Great Pyramid void is not an isolated anomaly, but part of a broad pattern of hidden architectural features that exist inside monuments that the scholarly community had assumed were fully understood. The ScanPyramids project itself scanned the bent pyramid at Dashur, Sneferu's famously angled monument, and detected anomalies in the pyramid's density distribution that are consistent with the presence of additional internal features beyond the known chamber system. The bent pyramid, with its 2 separate entrance systems and its dual internal chambers, is already one of the most architecturally complex pyramids in Egypt, and the detection of possible additional features suggests that its internal plan may be even more elaborate than the current model indicates. The implications for the dozens of other pyramids in the Nile Valley that have never been scanned with muon detectors are profound. The pyramids at Saqqara, at Abusir, at Lisht, at Dashur, at Meidum, at Lahoun, and at Hawara, each one a unique architectural experiment, each one built according to a different plan with different priorities and different structural solutions, are all candidates for muon tomography scanning. The technique could reveal hidden chambers, sealed passages, and structural features inside monuments that have been explored by conventional methods and pronounced fully understood. The cost of scanning is modest compared to the cost of excavation. The logistical requirements are manageable. The only barriers are institutional. The willingness of the Egyptian authorities to permit the placement of detectors at sensitive archaeological sites, the availability of funding to support the detector deployment and the data analysis, and the interest of the physics community in committing time and resources to archaeological applications of their technology. The GD Robot project, which explored the Queen's chamber shafts in 2011, represents another approach to the problem of investigating hidden spaces inside the Great Pyramid. The Jedi robot was a more advanced successor to Gantenbrink's Upuot, equipped with a camera that could see around corners by using a snake-like articulated arm, and it was designed to investigate the space behind the second blocking stone in the southern shaft. The images captured by the Jedi robot showed what appeared to be red ochre markings on the floor of the small chamber behind the blocking stones, markings that some scholars have interpreted as hieratic numerals or construction marks, and that others have dismissed as natural staining. The markings have never been definitively deciphered, and they represent yet another tantalizing clue about the Great Pyramid's interior, another piece of evidence that suggests the monument contains information that has not yet been read. The Queen's chamber shafts themselves remain one of the most profound mysteries of the Great Pyramid, and their relationship to the ScanPyramids void, if any, is unknown. The shafts are too narrow for a human to enter. They are blocked at both ends by limestone plugs. They do not reach the exterior of the pyramid. They appear to serve no ventilation function. Their alignment with specific stars in the night sky has been proposed but is debated, and their existence, sealed behind the original wall surfaces of the Queen's Chamber, invisible to every visitor from Al-Mamun in the 9th century to Dixon in the 19th, suggests that the builders of the Great Pyramid incorporated features into their design that were never intended to be seen, features whose purpose was theological or structural rather than functional, features that existed as part of the monument's cosmic program rather than as amenities for human use. This last point is crucial for understanding the ScanPyramids void. If the Great Pyramid's builders were willing to construct features that were invisible and inaccessible, features like the Queen's chamber shafts that were sealed behind the wall's surface, and that served a purpose that was comprehensible only within the framework of 4th Dynasty theology, then the existence of a large void that is invisible and inaccessible is entirely consistent with the builder's architectural philosophy. The void may not be a chamber in the sense that a modern visitor would recognize, a room with an entrance and a function that can be expressed in mundane terms. It may be a theological space, a feature of the pyramid's cosmic program that was built for the benefit of the dead king's spirit rather than for the convenience of the living, a space that was intended to exist in perpetuity, in sealed, pristine, undisturbed darkness, performing whatever function the builders assigned to it without any need for human access or human understanding. If this interpretation is correct, the void may be, in a sense, fulfilling its purpose at this very moment. Whatever the builders intended it to do, it has been doing for more than 4,500 years, in the darkness, in the silence, in the unchanging conditions of temperature and humidity that the surrounding limestone provides. The void does not know that it has been discovered. The muons pass through it as they have always passed through it, unaware of the detectors that are counting them. The void simply is, as it has been since the day the last block was placed above it, and the construction of the pyramid sealed it away from the world of the living forever. Its purpose, if it has one, is operating. Its function, if it has one, is being performed. And the question of what that purpose and that function might be is a question that the living may never be able to answer, because the answer was never intended for the living. It was intended for the dead, and the dead have kept the secret. The Great Pyramid is not merely a tomb, it is a machine. The Egyptian word for pyramid, meh, means place of ascension, and the entire architectural program of the Great Pyramid, from the orientation of its faces to the alignment of its passages, to the design of its chambers, was conceived as a mechanism for facilitating the dead king's transformation from a mortal being into an immortal one, from a human body into a being of light that could ascend to the sky and join the circumpolar stars in their eternal circuit around the celestial pole. The passages were designed to direct the king's spirit along specific trajectories. The chambers were designed to house the king's body in specific orientations. The shafts were designed to connect the king to specific celestial bodies. Every element of the pyramid's design had a theological purpose that went beyond its structural function, and the possibility that the void is one of these theological elements, a space designed not for human entry, but for spiritual transit, not for the storage of objects, but for the facilitation of the king's cosmic journey, is one that the archaeological community has been slow to consider, but that the evidence increasingly supports. The concept of sealed knowledge, knowledge that is embedded in a physical structure and that can only be accessed by penetrating that structure, is not unique to the Great Pyramid. It is a recurring theme in the archaeology of the ancient world, and the parallels illuminate the ScanPyramids void from angles that the Egyptian case alone cannot provide. The terracotta army of the first emperor of China, Qin Shi Huang, provides one of the most dramatic examples. The mausoleum of the first emperor, located near the city of Xi'an in central China, is one of the largest and most complex burial monuments ever constructed, and it is known to contain, according to ancient Chinese historical sources, a vast underground palace that has never been excavated. The historian Sima Qian, writing roughly a century after the emperor's death, described the underground palace as a microcosm of the empire, with rivers of mercury representing the Yangtze and the Yellow Rivers, a ceiling studded with pearls representing the stars, and crossbow traps designed to kill any intruder who penetrated the chamber. Modern soil testing has confirmed that the mercury levels in the soil above the burial mound are anomalously high, supporting Sima Qian's account of mercury rivers, but the Chinese government has not authorized the excavation of the underground palace, citing conservation concerns and the lack of technology capable of preserving the contents of the chamber once they are exposed to the atmosphere. The tomb of the first emperor is, like the ScanPyramids void, a sealed space whose existence is known, whose contents are a matter of informed speculation, and whose investigation is blocked not by technological incapability, but by the ethical and political decision to prioritize preservation over knowledge. The sealed tombs of the Valley of the Kings in Egypt provide another set of parallels. Despite more than 2 centuries of systematic excavation, the Valley of the Kings continues to yield new discoveries. The tomb designated KV63, discovered in 2005 by a team led by the American archaeologist Otto Schaden, was the first new tomb found in the valley since Howard Carter discovered the tomb of Tutankhamun in 1922, and its discovery demonstrated that the Valley of the Kings, like the Great Pyramid, still contains surprises despite being one of the most thoroughly investigated archaeological sites in the world. KV63 turned out to be not a royal tomb, but a storage chamber containing embalming materials, but its discovery proved the principle that major features can remain hidden in thoroughly investigated landscapes. Radar surveys conducted in the valley in recent years have detected additional anomalies in the bedrock that may indicate the presence of undiscovered tombs or chambers, though none of these anomalies has yet been confirmed by excavation. The broader lesson of these parallels is that the archaeological record is not a static, fully documented body of knowledge, but a dynamic, partially explored frontier that continues to yield new information with each advance in technology. The assumption that the major monuments of the ancient world have been fully explored and fully understood is not merely incorrect. It is dangerous because it leads to a complacency that discourages investment in the new technologies and the new methodological approaches that are needed to reveal what remains hidden. The ScanPyramids void is a wake-up call. It tells the archaeological community that the map is not complete, that the things we have found are not the totality of the things that exist, and that the technologies we need to find the rest are available or nearly available, and that the only barriers to their deployment are institutional, financial, and political rather than technological. The forgotten ones in this story are not the builders of the Great Pyramid, who are remembered in the cartouches on the relieving chamber walls and in the quarry marks on thousands of individual blocks. The forgotten ones are the physicists and the engineers who developed the technologies that made the discovery possible, the generations of particle physicists who built muon detectors for purposes that had nothing to do with archaeology, and who could not have imagined that their instruments would one day reveal a hidden space inside the most famous building on Earth. The discovery of the ScanPyramids void is a monument to the unpredictability of scientific progress, to the way that advances in one field can produce breakthroughs in another that neither field anticipated, and to the power of human curiosity to find new applications for old technologies long after the original inventors have moved on to other problems. The muon was discovered in cosmic ray experiments in the 1930s. It was studied in particle accelerators throughout the 20th century. It was used to image volcanoes, to inspect reactors, to scan shipping containers, and in 2017, 81 years after its discovery, it was used to find a hidden void inside a pyramid that was 4,500 years old. The muon did not know it was looking. The pyramid did not know it was being seen. And the void, sealed in darkness since the reign of Khufu, did not know that particles from the edge of the galaxy were passing through it, one by one, minute by minute, accumulating in detectors that were counting the silence that the void created in the cosmic rain. The numbers are striking. 10,000 muons per square meter per minute fall on the surface of the Earth. Each one has travelled from the upper atmosphere, a distance of roughly 15 kilometers, in a journey that lasts less than a millionth of a second. Each one passes through the Great Pyramid in an instant, faster than thought, faster than light could traverse the pyramid's interior if the interior were transparent. The muons do not slow down. They do not pause. They do not linger in the void or explore its surfaces or examine its contents. They pass through the stone and the void and the darkness, and emerge on the other side in less than a billionth of a second, having recorded, in the statistical pattern of their passage, in the subtle excess of particles that arrived at the detector where stone should have absorbed them, the shape of a space that no human being has ever entered and that no human eye has ever seen. The discovery of the void was made not by a human eye or a human hand, but by a mathematical analysis of the pattern of subatomic particles falling through stone, an analysis that required millions of individual particle detections accumulated over months of patient observation. And that was conducted by teams of physicists working in laboratories on 3 different continents. It is a discovery that belongs to the age of physics as much as it belongs to the age of archaeology, a discovery that was made possible not by human ingenuity alone, but by the universe itself, by the cosmic rays that have been bombarding the Earth since its formation, and that carry, in their secondary products, the power to see through stone, through mountains, through the densest materials that human civilization has ever shaped into monuments, and to reveal, in the silence of a detector readout, the presence of the emptiness that the stone was built to conceal. The question of what might be inside the void, if it is indeed a chamber rather than a structural feature, has generated speculation that ranges from the scientifically cautious to the wildly imaginative, and the range of speculation itself tells us something important about the power of the unknown to stimulate human imagination. The most conservative possibility is that the void is empty, a sealed space that was never intended to contain anything, and that has remained exactly as it was left by the builders, an empty room of air and stone and darkness that has no contents and no significance beyond its architectural function. This is the possibility that the archaeological establishment considers most likely, and it is the possibility that would produce the least dramatic outcome if the void were ever accessed. But even an empty void would be scientifically valuable, because the air sealed inside it would be a sample of the 4th dynasty atmosphere, trapped and preserved since the reign of Khufu, that could be analysed for its chemical composition, its isotopic ratios, and its content of biological material, including pollen, spores, and microbial DNA, that might provide information about the environment of the Giza plateau at the time of the pyramid's construction. An empty void would also preserve the surfaces of its walls in a state of unparalleled conservation, protected from the weathering, the vandalism, the soot deposits, and the abrasive contact with human hands and tools that have damaged every accessible surface inside the pyramid. If the walls of the void bear tool marks, construction marks, or any other evidence of the building process, they would be in pristine condition, untouched since the day the last block was placed. The more dramatic possibility is that the void contains something: a statue, a sarcophagus, a collection of funerary equipment, a set of inscriptions, a repository of objects that were placed there as part of the pyramid's theological program, and that have been sealed in perfect preservation conditions for more than 4,500 years. The precedent for this possibility exists. The boat pits beside the pyramid contained disassembled cedar boats in remarkable condition. The relieving chambers contained quarry marks and construction graffiti that are the only known inscriptions inside the pyramid. The Queen's chamber shafts contained blocking stones with copper fittings that may have had ritual significance. The Great Pyramid has a history of containing unexpected things in unexpected places, and the void, as the largest unknown space inside the monument, has the greatest potential for unexpected content. The possibility that has captured the most public imagination, and that the most cautious scholars are the most reluctant to discuss, is that the void might contain a second burial chamber, a chamber that was intended as the king's actual resting place, and that was sealed after the burial with such thoroughness that it has remained undetected for 4.5 millennia. This hypothesis, while speculative, is not without archaeological support. The Great Pyramid's known chamber system shows evidence of multiple changes of plan during construction, with the subterranean chamber apparently abandoned in favor of the Queen's chamber and the Queen's chamber apparently abandoned in favor of the King's chamber. The pattern suggests a builder's willingness to revise the internal plan during construction, and it raises the possibility that the King's chamber, which was robbed in antiquity and which contains only an empty granite sarcophagus, was not the final version of the burial plan, but an intermediate version that was itself superseded by a further revision whose location is the void. This hypothesis is extravagant. It is unsupported by direct evidence. It is the kind of speculation that responsible scholars avoid because it raises expectations that the evidence cannot currently meet. But it is not impossible, and the fact that it is not impossible, the fact that the Great Pyramid's internal architecture is complex enough and its construction history is uncertain enough to permit such a hypothesis without violating any known fact, is itself a measure of how much remains unknown about the most studied building in the history of the world. The forgotten ones in this chapter of the story are the instrument builders, the people who designed and constructed the muon detectors that made the discovery possible. The nuclear emulsion films used by the Nagoya team were manufactured by hand in a Japanese laboratory, each one a precision photographic instrument that required weeks of careful preparation and quality control before it could be exposed to the muon flux inside the pyramid. The scintillator hodoscopes used by the Kate team were assembled from thousands of individual scintillator strips, each one calibrated and tested to ensure that it would respond reliably to the passage of a single muon. The gas detectors used by the CEA team were custom-built instruments designed specifically for the ScanPyramids project, incorporating technology developed for the most advanced particle physics experiments in the world and adapted for field deployment in the harsh desert environment of the Giza Plateau. The people who built these instruments are not Egyptologists. They are not archaeologists. They are physicists and engineers whose names are listed in the author credits of the Nature paper, but who will never be remembered with the same fame as the Egyptologists whose interpretations of the void will shape the public understanding of the discovery. The instrument builders are the unsung heroes of the ScanPyramids project, the people whose technical skill and whose willingness to apply the tools of fundamental physics to a problem that was, by the standards of their didipacilin, decidedly applied rather than fundamental, made the discovery possible. The void waits. It has waited for 45 centuries. It can wait longer. The muons continue to fall through it, recording its shape in the statistical patterns of their passage, indifferent to the questions that its existence has raised and to the debates that its discovery has provoked. The void is not impatient. It is not curious about what happens outside its sealed walls. It simply is, as it has been since the day the builders sealed it, a space of darkness and silence and perfect stillness at the heart of the most famous monument on Earth, unknown for millennia, detected by subatomic particles, and still, despite everything that modern science has brought to bear on it, fundamentally, irreducibly, and perhaps permanently, a mystery. The imagination of absence is one of the most powerful forces in human cognition. We are drawn to sealed doors, to locked boxes, to spaces we cannot enter, and contents we cannot see. The void inside the Great Pyramid activates this cognitive impulse at a scale and a depth that no other archaeological mystery can match. The building is the most famous on Earth. The void is the largest unknown space inside it. The contents are inaccessible, the mystery is irreducible, and the pull of that mystery, the gravitational attraction of the unknown at the heart of the known, is powerful enough to draw the attention of physicists and Egyptologists and journalists and millions of curious people around the world, all of them drawn by the same fundamental human impulse, the need to know what lies behind the wall, beneath the surface, inside the sealed space that someone long ago decided that no one should ever see. The builders of the Great Pyramid understood this impulse. They designed the pyramid to resist it. They sealed the passages. They blocked the shafts. They concealed the entrances. They constructed an architecture of denial, a building designed not to reveal but to conceal, not to invite but to exclude, not to satisfy curiosity but to defeat it. and for 45 centuries, the architecture of denial has succeeded. The void remains sealed, the darkness remains unbroken, the secret remains kept. But the muons have pierced the denial, if only partially, if only statistically, if only enough to confirm the existence of the secret without revealing its content. The particles from the edge of the galaxy have told us that the Great Pyramid has a hidden space. They have not told us what the space contains. And the gap between what the particles have told us and what we want to know is the gap that drives the ongoing investigation, the continuing debate, and the enduring fascination that the Great Pyramid, the oldest and the greatest of all human monuments, continues to exert on the human mind. There is a moment, late at night, when the technical details of muon detection and the scholarly debates about construction hypotheses fall away, and the existential dimension of the discovery comes into focus. The Great Pyramid contains a void, a space, an absence. 30 meters of darkness, sealed inside an estimated 6 million tons of carefully quarried and precisely placed limestone, surrounded on every side by the densest and the most massive accumulation of construction material that the ancient world ever assembled into a single coherent structure. The void has been there since before the invention of alphabetic writing in Greece, since before the founding of Rome on the banks of the Tiber, since before the composition of the Vedas on the plains of northern India, since before the rise of the Shang dynasty in the Yellow River Valley of China, since before virtually every event that the modern world considers ancient. It has been there through every century of recorded human history, silent and sealed and unknown, while civilizations rose and fell, and the world changed beyond recognition around the monument that contained it. Let that sink in. The most studied building on Earth has a secret. The secret was kept for more than 4,500 years. It was revealed not by human exploration, but by subatomic particles that travel at nearly the speed of light. And the secret, now that it has been partially revealed, has generated more questions than answers, more uncertainty than clarity, more mystery than resolution. We know more than we knew before. We understand less than we thought we did. And the gap between knowing and understanding, between detection and comprehension, is the space where the void exists, not just physically inside the pyramid, but intellectually inside the discipline that studies it. The deeper truth of the ScanPyramids discovery is not about the void. It is about the limits of knowledge, about the boundaries that constrain even our most intensive investigations of the past, about the humbling realization that the things we do not know about the ancient world vastly outnumber the things we do. We have been studying the Great Pyramid for more than 200 years. We have measured it to the millimeter. We have photographed every surface. We have analyzed its stone with spectrometers. We have mapped its passages with laser scanners. We have sent robots into its shafts. We have counted the muons that pass through its mass. And we have found a void that we cannot explain, in a location that we cannot reach, with contents that we cannot determine, that has been there all along, waiting to be discovered by a technology that did not exist until the 20th century, and that was not applied to the pyramid until the 21st. This is not science fiction. This is the documented reality of archaeological investigation at the highest level of technological sophistication. And the lesson it teaches is not that technology has solved the mystery, but that technology has revealed the depth of the mystery, has shown us that the mystery is deeper than we thought, that the monument is more complex than we assumed, and that the builders of the Great Pyramid were capable of architectural feats that exceed our current ability to detect, to understand, or to explain. We assume that what we build will outlast us. The ruins suggest otherwise. Every monument is a bet against time, and time has never lost. But the ScanPyramids discovery adds a new dimension to this observation. The Great Pyramid has not merely outlasted its builders, it has outlasted our ability to understand it. The monument has survived. Our comprehension of it has not kept pace. We have been studying the Great Pyramid for 2 centuries, and it still has the power to surprise us, to confound us, to force us to admit that the most intensive investigation in the history of archaeology has been insufficient to reveal everything that the monument contains. The pyramid is winning, the archaeologists are catching up, and the void, Sealed in darkness at the heart of the monument is the scorecard, the permanent record of how much remains to be learned. The question of whether the void changes the Great Pyramid or merely changes our understanding of it is a question that illuminates the broader relationship between knowledge and reality in the study of the past. The pyramid is an object. The void is a feature of that object. Both have existed, unchanged, for more than 4,500 years. The discovery of the void did not create it. The muon detectors did not conjure it into existence. The void was there before the detectors were deployed, before the ScanPyramids project was conceived, before muon tomography was invented, before the muon was discovered, before physics existed as a discipline. The void is older than the science that found it, and the science, however sophisticated, has only revealed the void's existence. It has not revealed the void itself. The void remains in the darkness, unseen, untouched, as it has been since the builders sealed it. What has changed is our awareness. What has not changed is the reality. And the gap between our awareness and the reality, between what the detectors have told us and what the void actually is the gap that the next generation of investigation will need to close. The philosopher of science Thomas Kuhn wrote about the concept of the paradigm shift, the moment when the accumulated anomalies in a scientific field become so numerous and so significant that the existing framework can no longer accommodate them, and must be replaced by a new framework that can. The ScanPyramids void is an anomaly in the paradigm of Great Pyramid studies, a feature that the existing model of the pyramid's internal architecture did not predict and cannot explain. Whether this single anomaly is sufficient to trigger a paradigm shift remains to be seen, but the void, combined with the ongoing mysteries of the Queen's chamber shafts, the unexplained thermal anomalies on the pyramid's surface, and the persistent questions about the construction method, suggests that the existing paradigm is under strain, that the model of the Great Pyramid that has served Egyptology for more than a century is approaching the limits of its explanatory power, and that a new model, one that incorporates the void and the other anomalies into a more comprehensive understanding of the monument's design, may be needed. Let that sink in. The model that the world has used to understand the most famous building on Earth for more than 100 years may be incomplete. The map may need to be redrawn. The story may need to be retold. And the retelling, when it comes, will be driven not by new archaeological excavations, but by new physical measurements, not by shovels and brushes, but by muon detectors and endoscopic cameras, not by the traditional tools of the humanist, but by the experimental instruments of the physicist. The future of pyramid studies belongs to the muon. The grief moment of this story is not about what we have lost, it is about what we have not yet found. The void inside the Great Pyramid is not a ruin. It is not a monument that has been destroyed, or a chamber that has been looted, or a text that has been lost. It is a space that exists in a state of perfect preservation, sealed and protected by the very architecture that conceals it, waiting in conditions that no museum and no conservation laboratory can match for the technology that will eventually allow us to see what it contains. The grief is not the grief of destruction. It is the grief of tantalization, the exquisite frustration of knowing that something is there and not being able to see it, of standing beside the most famous building on Earth and knowing that it contains a space you cannot enter, a secret you cannot read, a mystery you cannot solve. This is not science fiction. This is the lived experience of every scholar who has absorbed the implications of the ScanPyramids data and who has felt the weight of the knowledge that the Great Pyramid is not fully known, that the map has a blank space, that the story has an unwritten chapter. The experience is humbling in a way that most encounters with the ancient world are not. It is disorienting in a way that forces a fundamental reassessment of what we thought we knew, and it is, in a paradoxical and deeply stirring way, exhilarating, because it means that the study of the Great Pyramid is not a closed book, that there are still genuinely new things to discover inside the most thoroughly investigated structure in the world, and that the future of Egyptology may hold surprises as dramatic as any that the past has produced. The American writer Annie Dillard once observed that how we spend our days is how we spend our lives. The observation applies to civilizations as well as to individuals. How a civilization spends its attention, what it chooses to investigate, what it chooses to ignore, what it chooses to protect and what it chooses to exploit, determines the kind of civilization it becomes. The decision to investigate the Great Pyramid with muon detectors rather than with drills was a decision about what kind of civilization we want to be. A civilization that extracts knowledge at the cost of destroying the things it studies. Or a civilization that develops technologies capable of extracting knowledge without destruction, that has the patience to wait for the right tools rather than the impulse to use the wrong ones, that values the integrity of the monument as much as the information the monument contains. The void will be investigated, it will be imaged, it will be understood. The technology that is needed to see inside it without penetrating its walls is being developed in laboratories around the world, driven by the same cosmic curiosity that has propelled human beings to explore every frontier they have ever encountered. The investigation will take time. It may take years. It may take decades. But the void has waited for 45 centuries. It can wait a little longer. And the patience that the investigation requires, the willingness to defer gratification, to resist the impulse to drill, to accept uncertainty in the present in exchange for preservation in the future, is itself a form of respect for the builders who sealed the void and who intended it, whatever its purpose, to remain sealed. The ancient Egyptians believed that the dead continued to exist as long as their names were spoken and their monuments were maintained. The speaking of the name was an act of creation, a ritual performance that sustained the existence of the dead across the boundary between the living and the dead worlds. The void inside the Great Pyramid is, in a sense, a name that has not yet been spoken, a feature of the monument that has not yet been identified, described, or incorporated into the understanding of the pyramid that sustains its cultural existence in the modern world. The comparison between the void and the sealed tombs of ancient Egypt is instructive in another way. The ancient Egyptians went to extraordinary lengths to protect the contents of their tombs from disturbance, designing complex anti-robbery systems of false passages, portcullis blocks, hidden entrances, and decoy chambers that were intended to prevent anyone from reaching the burial after it was sealed. The void inside the Great Pyramid may represent the ultimate expression of this protective impulse, a space so thoroughly sealed, so completely concealed within the pyramid's mass, that it has defeated every attempt to reach it for more than 4,500 years. If the void is a chamber, and if the chamber contains the remains of funerary equipment or the remains of a burial, then it is the most successfully protected space in the entire history of Egyptian funerary architecture, a space that has achieved what every other tomb in the Valley of the Kings and every other pyramid in the Nile Valley failed to achieve. Permanent, complete, unbroken security against intrusion by the living. The tomb robbers who penetrated the king's chamber and emptied the granite sarcophagus did not find the void. The treasure hunters who drove tunnels through the pyramid's mass did not encounter the void. The archaeologists who mapped every known passage and chamber did not detect the void. Only the muons found it, and the muons are not intruders. They are visitors from the cosmos, and they pass through the void without disturbing it, leaving it as sealed and as pristine as the day the builders closed it. The void awaits its name. It awaits its description. It awaits the moment when its existence is fully understood and fully integrated into the story of the Great Pyramid that the world tells itself. And until that moment comes, the void will remain what it is now. A question without an answer, a presence without an identity, a space without a name, sealed in the darkness at the heart of the most famous building on Earth. The comparison with other moments of paradigm-shifting discovery in the history of archaeology is instructive. When Howard Carter broke through the sealed doorway of Tutankhamun's tomb in 1922 and saw, by the light of a candle, the glint of gold in the darkness, he experienced a moment that has become the defining image of archaeological discovery in the popular imagination. Carter's discovery was dramatic, visual, and immediately comprehensible. Gold objects gleamed in the candlelight. The face of a king, dead for more than 3,000 years, stared back at the excavator through a mask of solid gold. The drama of the moment required no interpretation. It was self-evident. The ScanPyramids discovery is the opposite of Carter's moment in almost every respect. There was no doorway, there was no candlelight, there was no gold, there was no face staring back across the millennia. There was a statistical anomaly in a muon flux measurement, a pattern of excess particles detected by 3 independent instruments over a period of months, analysed by physicists using mathematical techniques that are incomprehensible to most archaeologists and to virtually all members of the general public. The discovery was not visual, it was numerical. It was not dramatic in the traditional sense. It was dramatic in the scientific sense, the sense in which a confirmed anomaly that overturns a century of established understanding is more dramatic, more consequential, and more transformative than any single object, however beautiful, found in any single tomb. The lack of visual drama has shaped the public reception of the discovery in ways that are themselves revealing. Carter's discovery of Tutankhamun's tomb generated worldwide media coverage that lasted for years and that transformed the public image of Egyptology into one of the most glamorous and most exciting disciplines in the world. The ScanPyramids discovery generated a brief burst of media attention that faded within weeks, as the difficulty of explaining muon tomography to a general audience and the lack of visual images of the void itself made the story difficult to sustain in a media landscape that rewards spectacle over substance. The void is, in media terms, unphotogenic. There are no images of it. There cannot be images of it because no one has seen it. The only visual representation of the void is a computer-generated density map, a false color image produced by mathematical analysis of muon data that shows a region of reduced density in the pyramid's mass as a bright spot against a darker background. The image is scientifically meaningful but visually uninspiring, and it has failed to capture the public imagination in the way that the golden mask of Tutankhamun captured it a century ago. The disparity between the scientific significance of the discovery and the public attention it has received is itself a commentary on the relationship between knowledge and spectacle in the modern world. The void inside the Great Pyramid is one of the most important archaeological discoveries of the 21st century. It has transformed our understanding of the most famous monument on Earth. It has demonstrated the power of physics technologies to reveal features of ancient structures that conventional archaeology cannot detect. And it has been largely forgotten by the general public within a few years of its announcement, overtaken by other news stories, other discoveries, other spectacles that were more immediately visual and more easily narrated. The void deserves better. It deserves to be remembered as what it is. The moment when the Great Pyramid, the oldest of the 7 wonders, the last wonder standing, revealed that it had been keeping a secret for 45 centuries, and that the secret, detected by particles from the edge of the galaxy, remains unsolved. The void challenges the modern obsession with visual evidence, with the assumption that seeing is understanding, that a photograph resolves a question, that an image settles a debate. The void cannot be photographed. It cannot be filmed. It cannot be rendered in any medium that the human eye can process directly. It exists only as data, as numbers in a spreadsheet, as statistical distributions in a muon flux analysis, as a region of elevated particle counts in a detector readout that requires specialized training to interpret, and that conveys its meaning not through visual impact but through mathematical analysis. The void is, in this sense, the anti-spectacle, the discovery that resists the visual logic of the media age, and that demands a different kind of attention, a slower kind of comprehension, a willingness to understand significance, without the aid of dramatic images or compelling visual narratives. The resistance of the void to visual representation is itself one of its most important characteristics, because it forces a confrontation with the limits of visual knowledge that the modern world is generally reluctant to face. We live in an image-saturated culture, a culture that processes information primarily through visual channels, and that tends to equate seeing with knowing, visibility with reality, appearance with truth, The void confounds this equation. It is real but invisible. It is there but unseen. It is the most important feature of the most famous building on Earth, and it cannot be represented in any image that would communicate its significance to a viewer who does not already understand the science behind its detection. The void demands that we trust the data rather than our eyes, that we accept the testimony of subatomic particles over the testimony of photographs, that we believe in the reality of something we cannot see, because the evidence for its existence, while invisible to the unaided human senses, is overwhelming in its statistical significance and its methodological rigor. This demand for trust in invisible evidence is itself a kind of lesson, one that extends far beyond the specific case of the Great Pyramid void. The most important truths about the universe are often invisible truths, truths that cannot be seen or photographed or rendered in images, but that can be detected by instruments and confirmed by mathematics. The void inside the Great Pyramid is a reminder that the real world is larger than the visible world, that the things that can be seen are a subset of the things that exist, and that the technologies we have developed to extend our perception beyond the limits of the unaided human senses are among the most important and most consequential achievements of our civilization. The muon detector is an instrument for seeing the invisible. The void is the invisible made real, and the discovery, the moment when the data revealed the presence of a space that no eye had seen for 45 centuries, is a testament to the power of human ingenuity to reach beyond the boundaries of perception and to touch, however lightly and however incompletely, the hidden architecture of the past, the spaces that were sealed, and the secrets that were kept, and the voids that were created by builders, whose purposes we are only now, 4.5 millennia later, beginning to detect and to interrogate and to struggle with the tools of 21st century physics to understand. The desert wind blows across the Giza plateau. The tourists photograph the Sphinx. The souvenir vendors call out their prices. The camels wait. And inside the pyramid, above the Grand Gallery, in a space that no human being has seen for more than 4,500 years, the void exists. The muons pass through it. The darkness fills it. The silence within it has never been broken by a human voice. And the pyramid, ancient and massive and patient, keeps its secret as it has always kept its secrets, with the perfect indifference of stone that was shaped to last forever, and that has, so far, kept its promise. Step back now from the muon data and the scholarly debates and the competing hypotheses and the sealed spaces and the subatomic particles and look at the full arc of what has been described. Because the discovery of the void inside the Great Pyramid is not, in the end, merely a story about a single monument and a single scanning project. It is a story about the relationship between technology and knowledge, about the way that advances in one field of human endeavor can produce breakthroughs in another that neither field anticipated, and about the implications of this relationship for the future of our understanding of the past, and for the technologies and the institutional structures that will shape that understanding in the decades and the centuries to come. We live in a world that has produced technologies of extraordinary penetrating power, technologies that were originally developed for purposes that have nothing to do with archaeology, but that have proven, when applied to the monuments of the ancient world, to be capable of revealing features and structures that centuries of conventional investigation had failed to detect. Muon tomography, ground-penetrating radar, LiDAR, infrared thermography, electrical resistivity tomography, magnetometry, and a growing suite of other geophysical and remote sensing technologies. Each of these offers a different way of seeing inside or beneath structures and landscapes that are completely invisible and entirely opaque to the unaided human eye. The application of these technologies to archaeology is still in its early stages, and the ScanPyramids project has demonstrated, with the most spectacular possible proof of concept, that the potential for new discoveries is enormous. The implications extend beyond Egypt to every ancient civilization that built in stone, in earth, in brick, or in any other material that is dense enough to produce a measurable contrast with the voids it may contain. The pyramids of Mesoamerica, the temples of Southeast Asia, The fortifications of the Roman frontier, the burial mounds of the European Bronze Age, the subterranean cities of Cappadocia, every one of these categories of monument is a candidate for non-invasive scanning, and every one of them may contain hidden features that conventional archaeology has not detected and cannot detect without the application of technologies that have only recently become available. The revolution in non-invasive archaeological investigation that the ScanPyramids project has catalyzed represents a fundamental and potentially irreversible shift in the relationship between archaeology and the past. For 2 centuries, archaeology has been primarily an extractive discipline, a field that gains knowledge by removing material from the ground, by excavating, by digging, by physically penetrating the structures and the deposits it studies. Every excavation destroys the thing it studies. A deposit that has been excavated can never be excavated again. The stratigraphic relationships, the spatial associations, the three-dimensional context that gives artifacts their meaning are consumed by the act of excavation and preserved only in the excavator's records. Records that are inevitably selective, inevitably incomplete, and inevitably shaped by the excavator's assumptions about what is important and what is not. The non-invasive approach reverses this destructive relationship. Instead of extracting material from the past, the non-invasive approach extracts information from the material using technologies that can image the interiors of structures without disturbing their fabric, that can map the subsurface of landscapes without breaking the ground, and that can detect hidden features without destroying the contexts that give those features their meaning and their value. The ethical dimensions of this shift are profound and far-reaching. The great excavations of the 19th and early 20th centuries, the excavations that produced many of the most spectacular discoveries in the history of archaeology, were conducted with methods that would be considered unacceptably destructive by modern standards. Howard Carter's excavation of Tutankhamun's tomb, for all its meticulous documentation, involved the removal of hundreds of objects from the contexts in which they had been placed more than 3,000 years before, contexts that can never be reconstructed because the spatial relationships between the objects were disrupted by the act of removal. Heinrich Schliemann's excavation of Troy destroyed layers of occupation that contained information that Schliemann's methods were incapable of recording, and that is now permanently lost. The extraction of knowledge from the archaeological record has always involved the destruction of the record itself, and the accumulating awareness of this destruction has driven the modern discipline toward non-invasive techniques that promise to break the cycle of destruction that has characterized archaeological investigation since its inception. The application of these technologies to archaeology represents only the beginning of what may be a broader transformation in how human civilization investigates and understands its own past. The technologies are improving rapidly. Muon detectors are becoming smaller, cheaper, and more sensitive with each generation of development. Ground-penetrating radar systems are achieving deeper penetration and higher resolution as signal processing algorithms become more sophisticated. LiDAR scanning, which has already revolutionized the archaeology of forested regions by revealing structures hidden beneath the jungle canopy, is being applied to new environments and new scales of investigation. And artificial intelligence systems, trained on archaeological data from thousands of sites, are beginning to identify patterns and anomalies in geophysical survey data that human analysts might miss, accelerating the pace of discovery and expanding the scope of investigation beyond what any individual researcher or team could achieve. The question is not whether these technologies will produce new discoveries. They will. The question is whether the institutional structures of archaeology, the funding agencies, the government, regulatory bodies, the university departments, and the professional organizations that govern the discipline are prepared for the flood of new data and new discoveries that the non-invasive revolution will produce. The ScanPyramids project was a single project at a single site, and it produced a discovery that has occupied the scholarly community for years, and that will continue to generate research and debate for decades to come. Imagine the same technology applied to dozens of sites, to hundreds of pyramids, to thousands of ancient structures around the world. The volume of data would be enormous. The number of anomalies detected would be vast. The demand for interpretation, for verification, for follow-up investigation would exceed the capacity of the current archaeological establishment by orders of magnitude. The non-invasive revolution is not merely a change in technology, it is a change in scale that will require corresponding changes in the institutional structures that support archaeological research. The comparison with medical imaging is instructive and illuminating. Before the invention of X-rays in 1895, the internal structure of the human body could only be studied by cutting it open, a procedure that was invasive, dangerous, and often fatal. The X-ray transformed medicine by allowing physicians to see inside the body without cutting, to diagnose fractures and tumors and foreign objects without the risks of exploratory surgery. Subsequent developments, including CT scanning, MRI, ultrasound, and PET scanning, have extended the principle of non-invasive imaging to every organ system and every tissue type in the body, producing a revolution in diagnostic medicine that has saved millions of lives and that has fundamentally transformed the relationship between physician and patient. The non-invasive revolution in archaeology promises a transformation of comparable scope, though operating at a different scale and in a different domain. Just as X-rays allowed physicians to see inside the body for the first time, muon tomography and its associated technologies are allowing archaeologists to see inside ancient monuments for the first time, revealing features and structures that were previously hidden behind walls of stone that no one could penetrate without destroying. The analogy extends to the ethical framework that governs the use of these technologies. Medical ethics prohibits unnecessary surgery, requiring physicians to exhaust non-invasive diagnostic options before resorting to invasive procedures. Archaeological ethics is evolving in the same direction, increasingly requiring researchers to exhaust non-invasive investigation options before resorting to excavation that will destroy the deposits and the contexts it studies. The ScanPyramids project is a model for this ethical evolution, demonstrating that non-invasive technologies can produce discoveries of the first importance without disturbing a single stone, and establishing a precedent that future projects will be expected to follow. The precedent is not merely methodological, it is ethical. It establishes the principle that the most important archaeological discoveries can be made without destruction, that the choice between knowledge and preservation is a false choice, and that the technologies of the 21st century, technologies that were developed in physics laboratories and engineering workshops for purposes that have nothing to do with the ancient world, have made it possible to have both, to extract information from the past without consuming the past in the process. This is a new possibility. It has not existed before, and the ScanPyramids project, by demonstrating its viability at the most important archaeological site in the world, has made it impossible for future researchers to claim that non-invasive investigation is impractical, insufficient, or incapable of producing results of the first importance. The void proves otherwise. The data proves otherwise. The 3 independent detector systems prove otherwise. And the pyramid, still standing, still intact, still containing its secret in the sealed and undisturbed darkness of the void, proves that knowledge and preservation can coexist, that the past can be investigated without being destroyed, and that the most powerful argument for patience is a discovery that patience made possible. The Great Pyramid Void is the most compelling demonstration of this promise that has ever been produced. A hidden space was detected, characterized, and confirmed without moving a single stone, without drilling a single hole, without disturbing a single grain of the dust that has accumulated on the surfaces of the pyramid's interior over 45 centuries. The knowledge was gained without cost to the monument. The information was extracted without damage to the source. The technique worked, and it worked on the most important archaeological target in the world, under the most intense scrutiny that the scholarly community could provide, and it produced a result that has been accepted by the scientific establishment as genuine, as significant, and as worthy of the further investigation that the technique itself has made possible. The implications extend beyond Egypt to every ancient civilization that built in durable materials. The pyramids of Mesoamerica, the temples of Southeast Asia, the fortifications of the Roman frontier, the burial mounds of the European Bronze Age, the megalithic monuments of the Atlantic seaboard. Every one of these categories of monument is a candidate for non-invasive scanning, and every one of them may contain hidden features that conventional archaeology has not detected and cannot detect without the application of technologies that have only recently become available or that have not yet been developed. The non-invasive revolution also has implications for the relationship between science and the humanities, between the quantitative disciplines that produce the scanning technologies and the interpretive humanistic disciplines that provide the cultural and historical frameworks within which the discoveries are understood. The ScanPyramids project succeeded because it brought together physicists who understood muon detection and Egyptologists who understood pyramid architecture, creating an interdisciplinary collaboration that was greater than the sum of its parts. The physicists could detect the void. The Egyptologists could interpret it. Neither group could have made the discovery alone. The future of archaeological investigation will require more such collaborations, more bridges between the sciences and the humanities, more institutional structures, and more formal mechanisms that facilitate the exchange of knowledge, methodologies, and perspectives between disciplines that have traditionally operated in isolation from one another. The ScanPyramids project has opened a door. The archaeological community has not yet fully walked through it, but the void inside the Great Pyramid, silent and sealed and waiting in the darkness, is the most persuasive possible argument for walking through that door and for committing the resources, the institutional will, and the interdisciplinary collaboration needed to apply non-invasive technologies to the ancient world on the scale that the archaeological record demands and deserves. The Great Pyramid of Khufu stands on the Giza Plateau as it has stood for more than 4,500 years, its massive limestone bulk absorbing the heat of the desert sun during the day and releasing it slowly into the cool night air, its outline visible from kilometers away, its presence felt by every person who has ever stood in its shadow and looked up at the ascending courses of stone that rise, tier upon tier, toward a summit that was once capped with a gleaming pyramidion of polished stone, and that is now a rough, flat platform where tourists stand and photograph themselves against the Cairo skyline. Inside the pyramid, in the darkness beyond the known chambers and the mapped passages and the documented shafts, the void exists. It has existed since the reign of Khufu. It has existed through the rise and fall of every civilization that has stood on the plateau and looked up at the pyramid's silhouette against the Egyptian sky. It has existed through the sack of Thebes, through the fall of Rome, through the rise of Islam, through the Crusades, through the Ottoman conquest, through Napoleon's expedition, through the British occupation, through Egyptian independence, through the modern age of tourism and satellite imagery and global media. The void has outlasted them all. It has outlasted every person who has ever entered the pyramid, every scholar who has ever studied it, every theory that has ever been proposed about its design and its purpose. The void is older than every interpretation of the pyramid. It is older than Egyptology itself. It will be there when the current generation of scholars has retired, and when their successors have retired, and when the technologies that are being developed to investigate it have been superseded by technologies that no one alive today can imagine. The question this documentary began with was what was discovered inside the Great Pyramid in 2017. The answer is that a void was discovered, a large previously unknown space, roughly 30 meters long, located above the Grand Gallery, detected by muon tomography, confirmed by 3 independent detector systems, and published in the journal Nature with the measured precision and the deliberate understatement that characterizes the most consequential scientific announcements. The void is real, its nature is unknown, its purpose is undetermined, its contents, if any, are inaccessible, and its existence has transformed our understanding of the Great Pyramid from a fully mapped monument with no remaining architectural secrets to a partially mapped monument with at least one major unknown feature and possibly more. The deeper answer is that what was discovered in 2017 was not merely a void inside a pyramid. It was a void in our knowledge, a gap in our understanding, a blank space on a map that we thought was complete. The discovery proved that the most intensively studied structure in the history of the world still has the capacity to surprise us, that the technologies we have been using to study the past have been inadequate to the task of revealing everything the past contains, and that the monuments of the ancient world, even the most famous and the most thoroughly investigated among them, are deeper and more complex and more mysterious than we assumed. The void is a corrective. It is a reminder that the past is larger than our understanding of it, that the things we have found are a fraction of the things that exist, and that the appropriate response to the ancient world is not the confidence of the expert who believes the map is complete, but the humility of the explorer who knows that the territory extends beyond the edges of every map ever drawn. The void has changed the Great Pyramid, not physically. The pyramid is the same mass of limestone it has always been. The void has been there since the day the pyramid was completed. Nothing has moved, nothing has changed. But the human understanding of the pyramid has changed, permanently and irrevocably, because the void has demonstrated that our understanding was incomplete, that the architectural model we had painstakingly constructed over more than a century of investigation was a partial representation of a reality that is more complex than the model could accommodate, and that the Great Pyramid, for all its fame and all its familiarity, remains a building that has not been fully explored, a monument that has not been fully understood, and a mystery that has not been fully solved, and that may not be fully solvable with the technologies that are currently available to archaeological science. The muons continue to fall, 10,000 per square meter per minute, raining down from the upper atmosphere, passing through the limestone blocks, passing through the granite beams, passing through the known chambers and the known passages and the sealed shafts and the hidden void, passing through the darkness where no light has reached for 45 centuries, and emerging on the other side, carrying in the statistical pattern of their passage, the outline of a space that the builders sealed and that the universe, through the medium of its own fundamental particles, has begun, slowly and incompletely and tantalizingly, to reveal. There is a final image that deserves to be held in the mind as this story ends. It is the image of a single muon, a subatomic particle born in the collision of a cosmic ray with an atom in the upper atmosphere, travelling downward at nearly the speed of light, penetrating the limestone surface of the Great Pyramid, passing through course after course of carefully laid stone, entering the void, crossing 30 meters of darkness in a fraction of a nanosecond, emerging from the void, continuing downward through more stone, and arriving at a detector in the Queen's chamber, where it is recorded as a single count in a dataset of millions, a single data point that contributes, along with millions of others, to the statistical image of a space that the builders sealed 45 centuries ago. The muon does not know it has made a discovery. The detector does not know it has recorded a secret. The pyramid does not know it has been seen. Only the physicists who analyze the data, who aggregate the millions of individual counts into a density map, and who identify the bright spot that indicates the void, only they understand what the particle has revealed. And even they do not understand everything. They know the void is there. They do not know what it means. The particle has delivered a fact. The meaning remains sealed. The discovery changes nothing about the pyramid's physical reality. The pyramid is the same structure it was before the muon detectors were deployed. The void has been there since the day the pyramid was completed. The muons have been falling through it since the first cosmic ray struck the upper atmosphere above the Giza plateau, billions of years before the first stone was quarried. What has changed is our awareness, our understanding, that the building contains something we did not know about, that the map we drew was incomplete, and that the monument we thought we had fully explored still had a secret to reveal. The change is in us, not in the pyramid, and the change, once it has occurred, is permanent. we will never again look at the Great Pyramid with the comfortable assurance that its interior is fully known. We will always know that there is a space inside it that we have detected but not seen, that we have measured but not entered, that we have identified but not understood. The void has become part of our understanding of the pyramid, and it has changed that understanding from a closed system to an open one, from a completed puzzle to an incomplete one, from a solved problem to an unsolved mystery. The void is there, it is real, it is waiting. The pyramid will endure. It has endured for more than 4,500 years, through every century of human history, through the rise and fall of every civilization that has existed since its construction, and it will endure for centuries, perhaps millennia, more. The void will endure with it, sealed inside the pyramid's mass, waiting in the darkness for the light that will eventually come. When the technologies of the future develop the means to image its interior without breaching its walls, to see what the builders sealed away, to read the message, if there is a message, that has been waiting in the silence since before the dawn of classical civilization. And the Great Pyramid, the oldest and the most enduring and the most mysterious of all human monuments, is not yet finished telling its story. The void is part of that unfinished story. It is the chapter that has not yet been written, the page that has not yet been read, the secret that has not yet been told. And the pyramid, patient and massive and enduring, will hold its secret until the world is ready to receive it.